Hello there, and welcome to Nightfall Science. Tonight, we drift beyond distant galaxies and cosmic horizons, exploring what it would truly take to cross the observable universe and why cosmic expansion places its farthest regions forever beyond reach. Let your shoulders ease, and let your eyes grow heavy as the universe quietly expands. Let's begin. When people imagine the edge of the universe, they often picture a boundary, a final wall, a distant surface where space simply stops. Beyond it, perhaps nothing. No stars, no galaxies, no direction, only an ending. But the real universe is stranger and quieter than that. The edge we speak about is not known to be a physical edge at all. It is a horizon, a limit created by time, distance, and the speed of light. It marks the farthest region from which information has had enough time to reach Earth. Everything beyond that horizon may still exist. It may contain galaxies, stars, planets, and perhaps regions as rich and complex as the part of the cosmos we can observe. But their light has not reached us. Some of it may never reach us. To understand why, begin with one simple idea. Looking into space is looking into the past. Light does not arrive instantly. It moves through empty space at nearly 300,000 kilometers per second. That speed is enormous. A beam of light could circle Earth more than 7 times in 1 second. Yet the universe is so vast that even light needs years, millions of years and billions of years to cross it. The moon is close enough that its light reaches Earth in a little over 1 second. When the moon is observed, it appears not exactly as it is now, but as it was a little more than 1 second ago. Sunlight takes roughly 8 minutes to reach Earth. The sun seen in the sky is therefore the sun from 8 minutes in the past. If it changed suddenly, Earth would not know until that light arrived. The nearest star system beyond the sun is more than 4 light-years away. Its light begins the journey years before reaching human telescopes. A galaxy 1 million light-years away appears as it was 1 million years ago. A galaxy 10 billion light-years away appears from an age when the universe itself was much younger. Every telescope is partly a time machine, not a machine that travels backward. A machine that receives ancient information. The deeper astronomers look, the earlier the universe appears. This creates the first limit. The universe has a finite observable history. Current cosmology places its age at roughly 13.8 billion years. Light cannot have traveled toward Earth for longer than the universe has existed. At first, this seems to suggest that the observable universe should have a radius of about 13.8 billion light-years. Light travels for 13.8 billion years, so the most distant visible regions should be 13.8 billion light-years away. But this is not the full picture. Space has expanded while the light was traveling. The distant region that released the ancient light did not remain at the same distance. As the light crossed the cosmos, the space between large groups of galaxies continued stretching. The source moved farther away through that expansion. The journey lasted billions of years. During that time, the universe became much larger. Because of this, the present distance to the most distant observable matter is much greater than 13.8 billion light-years. The radius of the observable universe is about 46 billion light-years in every direction. Its full observable diameter is therefore around 93 billion light-years. This does not mean light traveled faster than light. It means the distance changed while the light traveled. Imagine a small mark moving across the surface of a rubber sheet. As the mark moves, the sheet stretches beneath it. The mark still moves at its normal speed relative to the nearby surface, yet the total distance between the starting point and destination can grow during the journey. The light crossing the universe experiences something conceptually similar. It always moves locally at the speed of light, but the space through which it travels expands. The distant matter that emitted the light is now much farther away than it was at emission. This is one reason cosmic distances can feel difficult. Several different distances can describe the same object. There is the distance the light traveled, the distance the source was from Earth when the light began its journey, the distance the source would be from Earth now within the expanding universe. These values are not identical. Everyday life rarely requires such distinctions. A road usually does not stretch dramatically while someone drives across it. Cosmic space does. The observable universe is therefore not simply a sphere of light that traveled through a static emptiness. It is a sphere shaped by the history of expansion. Earth lies at the center of the observable universe from our perspective. But this does not place Earth at the physical center of everything. Any observer in a distant galaxy would also see themselves near the center of their own observable universe. Light reaches every observer from all directions. Each location has its own horizon. Imagine standing in thick fog. A circular region remains visible around you. The visible circle is centered on your position. Another person far away stands at the center of a different visible circle. Neither person occupies the center of the entire landscape. They occupy the center of what they can see. The cosmic horizon works in a similar way, though the reason is not fog. It is the finite travel time of information. A civilization billions of light years away may observe regions Earth can never see. At the same time, Earth can observe regions beyond that civilization's own horizon. The two observable universes overlap partly, but not completely. There may be galaxies visible to them that are forever outside our view. There may be galaxies visible to us that are forever outside theirs. The universe experienced from one location is only one window into a much larger whole. How much larger? No one knows. The entire universe may be only modestly larger than the observable region. It may be unimaginably larger. It may even be infinite. Measurements show that space appears very close to geometrically flat on enormous scales. But flatness does not prove infinity. A surface can appear flat locally, while possessing a much larger global structure. Earth's surface feels flat when viewed across a small field. Only over great distances does its curvature become clear. The full shape of the universe may be beyond what present observations can determine. The observable horizon prevents direct inspection of the whole. This means the phrase "edge of the universe" often describes the edge of observation rather than the edge of existence. It is the boundary of received information, not necessarily the boundary of space. There may be no physical wall to reach, no final galaxy floating beside an empty exterior, no sign saying the universe ends here. Even if a spacecraft could travel toward the observable horizon, that horizon would not behave like a fixed destination. It depends upon the observer. As the spacecraft moves, its observable region changes. New regions may come into view. Other regions remain inaccessible. The horizon belongs to a position and a moment. It is not one stationary shell waiting far away. A horizon can be real without being a material object. Earth's ocean horizon is a familiar example. A ship sails toward the line where sea and sky appear to meet. The line moves farther away. The ship never reaches the visual horizon as a place. It reaches regions that once appeared near the horizon. Then a new horizon surrounds it. The cosmic horizon is far more complex, but the central idea is similar. A limit of visibility is not always a location that can be touched. Suppose a spacecraft could move at almost the speed of light. It leaves Earth and heads toward one of the most distant visible galaxies. The journey would already be difficult beyond anything current technology permits. But imagine the engineering problem is solved. The craft accelerates. Stars pass slowly at first. Then the outside universe appears transformed by relativistic effects. Still, the target does not wait quietly. The expansion of space continues. The galaxy may be carried farther away. Depending upon its current distance, the craft may never reach it. Some galaxies visible today are already beyond what any signal sent from Earth now can ever reach. Their ancient light reaches us. But the present version of those galaxies is separated from Earth by expanding space so rapidly that our future message cannot close the distance. This creates a strange relationship. Earth can see places it can never visit. Human telescopes receive their past. But no spacecraft launched now can reach their future. The light arriving today began when those galaxies were much closer in the cosmic sense. During its journey, expansion carried them farther away. Their ancient photons complete the trip. A new photon sent from Earth faces a different universe. A larger one. An accelerating one. The route is no longer passable in the same way. This is one of the quietest separations in cosmology. Visibility does not guarantee accessibility. Something can be seen clearly, while remaining forever beyond physical reach. This is not because the spacecraft engine is weak. Even an ideal signal traveling at the speed of light may fail. The limitation comes from the changing geometry of space. The expansion of the universe is not merely the movement of galaxies through a fixed emptiness. On the largest scales, The distances between unbound galaxies increase because space itself expands. Nearby objects do not expand noticeably in this way. Atoms are held together by electromagnetic forces. Planets remain in solar systems because of gravity. Stars remain in galaxies. Many galaxies remain in groups and clusters. Local forces overcome cosmic expansion. But across the vast spaces between distant galaxy groups, expansion dominates. The greater the distance, the more expanding space lies between the observer and the remote object. A galaxy twice as distant generally recedes more rapidly through the Hubble expansion. Far enough away, the distance can increase faster than light. This statement often sounds like it violates relativity. It does not. Relativity prevents ordinary objects from moving locally through space faster than light. But the total distance between remote regions can increase faster than light because the space between them is expanding. No galaxy needs to race past nearby space at an impossible speed. Each local region behaves normally. Across billions of light years, the combined expansion produces a separation rate exceeding the speed of light. This is why faster-than-light expansion does not provide a simple engine for travel. It is not a current that a ship can easily ride toward the edge. It is the changing scale of cosmic distance. A traveler remains limited by local physics. The universe around the traveler can still expand in ways that make a destination unreachable. There are several cosmic horizons, each describing a different limitation. The particle horizon marks the farthest distance from which light has had time to reach us since the early universe. It defines the observable universe. Another horizon concerns the farthest places from which signals sent now may ever reach Earth in the future. And another concerns the farthest regions that signals sent from Earth now may ever influence. These boundaries are not identical. The observable universe includes objects whose light is reaching us today, even though their current state may already lie beyond any future communication. A galaxy can therefore exist inside the observable universe, but outside the reachable universe. It appears on our maps. Its ancient image can be studied, yet it no longer belongs to our possible future. The region humanity can ever influence is far smaller than the region humanity can currently observe. Even with light-speed communication, only part of the visible cosmos remains causally connected with Earth's future. The rest is slipping beyond contact, not vanishing immediately. Its old light continues arriving. For a very long time, distant galaxies remain visible, but the information becomes increasingly ancient. The galaxies themselves continue changing beyond our reach. Stars form, stars die, planets orbit. Perhaps civilizations rise and disappear. Earth receives none of their later history. The visible image becomes a final chapter from a place still existing, but no longer able to send anything that will ever arrive here. Cosmic acceleration deepens this separation. The expansion of the universe is not simply continuing. On very large scales, it is accelerating. The cause is represented in modern cosmology by dark energy. Its exact nature remains uncertain, but its observed effect is that distant unbound regions are separating at an increasing rate. As time passes, more galaxies cross beyond our future horizon. Their light becomes stretched to longer wavelengths. Their signals grow fainter. Eventually, they disappear from practical observation. Far in the future, observers within the gravitationally bound local group may see a much emptier sky. The Milky Way and Andromeda will have merged long before then. Nearby companion galaxies will remain part of one large gravitationally bound system, but distant galaxies outside that system will continue receding. Their light will fade and redshift. Future astronomers may no longer see the broad cosmic web that modern telescopes reveal. They may live in what appears to be an isolated island of stars. Evidence of the wider expanding universe could become difficult to recover. Humanity exists during an unusual observational era. The universe is old enough for galaxies, stars, planets, and complex chemistry, yet still young enough that distant galaxies remain visible across enormous scales. The cosmic history of expansion can be studied. The afterglow of the early universe can be measured. The wider structure remains open to observation. This does not make the present moment uniquely important in a mystical sense, but it gives modern cosmology access to evidence that may not remain visible forever. The observable universe is not a permanent collection. It changes. New light enters from regions whose signals have been traveling toward us. Other regions become unreachable in the future. The horizon evolves with cosmic time. When the universe was younger, the observable region was smaller. Less time had passed for light to travel. As time continued, more distant information arrived. The observable volume grew, but accelerated expansion means the relationship is not simply that everything will eventually become visible. Some regions remain permanently outside contact. The horizon grows in one sense while future communication shrinks in another. Cosmology contains several layers of distance and possibility at once. This is why reaching the edge cannot be understood as building a faster rocket alone. The destination is not a fixed wall. The universe changes during the journey. The horizon moves with the observer. The expansion alters distances. The speed of light limits information, and cosmic acceleration removes regions from possible contact. A traveler may cross billions of light years and still remain nowhere near an ultimate boundary. If the entire universe is infinite, there is no outer boundary to reach. If it is finite but unbounded, travel may continue without encountering an edge, much as movement across Earth's surface continues without finding an end to the surface. The geometry may curve through dimensions that are difficult to picture. A spacecraft could move forward indefinitely without reaching a wall. The phrase edge may belong more to human imagination than to cosmic structure. Human experience is filled with containers. Rooms have walls, countries have borders, objects have surfaces, stories have endings. It feels natural to ask what lies outside the universe. But the universe is not known to be an object sitting inside a larger ordinary room. Space is part of the universe. Asking what lies outside all space may not have a meaningful answer within current physics. It can resemble asking what lies north of the North Pole. The question uses a direction that no longer continues in the expected way. This does not prove there is no deeper reality. It means ordinary spatial language may fail. The universe may possess a shape without needing an external space around it. Its geometry can be defined internally: distances, angles, curvature, expansion. No outside viewpoint is required. A creature living only on a surface can measure the surface's geometry without leaving it. Likewise, cosmology studies the universe through relationships measured from within. There is no known platform beyond everything from which the whole cosmos can be viewed. Every observer remains part of the system being observed. This makes the journey to the edge partly a journey into the limits of language. Far, fast, outside, boundary, now. These words work well in ordinary life. Across cosmic scales, each becomes more complicated. There is no universal cosmic now, shared simply across all distances. Light travel means every observation samples another time. Relativity means different observers can divide space and time differently. Expansion means distance depends upon the cosmological model and the chosen definition. A traveler asking how far remains to the edge first needs to decide which edge. The current observable horizon from Earth, the traveler's future horizon. The boundary of matter created by the early universe. A physical boundary of the entire cosmos if one exists. Each question has a different answer. Some may have no answer available to observation. The most distant light humanity can detect does not come from the first stars. It comes from an earlier era. The cosmic microwave background. A faint glow arriving from every direction. This light was released when the universe was about 380,000 years old. Before that time, the cosmos was filled with hot, ionized matter. Light scattered constantly from free electrons. Space was not transparent in the way it is now. As the universe expanded and cooled, electrons joined atomic nuclei. Photons could begin traveling freely. Those ancient photons have crossed the universe ever since. Today, expansion has stretched them into microwave wavelengths. The cosmic microwave background forms a kind of visual surface around us. Not a solid wall, not the edge of space. It is the oldest light that can travel freely to present-day telescopes. Beyond it lies earlier cosmic history. But ordinary light cannot reveal that era directly, because the early universe was opaque. This is another horizon, a limit of electromagnetic sight. Other messengers may reach deeper. Neutrinos from the early universe. Gravitational waves produced during extremely early events. These are difficult to detect. Future instruments may reveal information from times earlier than the cosmic microwave background. The horizon of knowledge can move as technology changes. But no instrument can escape every physical limit. Some information may remain permanently inaccessible. The universe contains regions and eras separated from us, not by lack of engineering alone, but by causality. No signal can arrive. No observation can be made. No journey can connect them. This does not make cosmology hopeless. It makes the observable region more precious scientifically. Within it are hundreds of billions of galaxies, perhaps far more depending upon how faint populations are counted. Each galaxy may contain billions of stars. The unreachable edge is not required for wonder. The accessible window already exceeds ordinary imagination. Even crossing the Milky Way would challenge any technology based upon known physics. The galaxy is roughly 100,000 light-years across. A beam of light needs about 100,000 years to cross it. A spacecraft moving at 1% of light speed would need around 10 million years, ignoring acceleration and obstacles. The nearest major galaxy, Andromeda, lies about 2.5 million light-years away. At the speed of current spacecraft, the journey would take far longer than human civilization has existed. The edge of the observable universe is not simply one more difficult destination. It is a distance category beyond ordinary travel. Before discussing the farthest galaxies, a traveler must first solve the problem of crossing one galaxy, then the space between galaxies, then the changing expansion of the universe, then the horizons that no engine can cross. The journey becomes not only technological, it becomes cosmological, and this is where the true story begins. The edge of the observable universe is not waiting like a cliff in the dark. It is created by what light has been able to do since the beginning of cosmic history. It surrounds every observer differently. It moves as time passes, and some of the galaxies near it are already beyond any message humanity could ever send. The next part of this journey will explore what happens when a spacecraft attempts to approach the speed of light, how time changes for the traveler, and why relativity can shorten an experienced journey without allowing the universe's ultimate horizons to be crossed. A spacecraft heading toward the farthest visible galaxies would face its first great barrier long before cosmic expansion became important. The barrier is the speed of light. Light moves through empty space at approximately 300,000 kilometers per second. Nothing with mass can be accelerated to that speed using known physics. A spacecraft may approach it very closely, but it cannot reach it. This limit comes from special relativity. As the craft accelerates, its motion changes the relationship between distance, time, energy, and momentum. At ordinary speeds, these effects are extremely small. Cars, aircraft, and even most spacecraft move far too slowly for relativity to become noticeable in daily life. But near the speed of light, the effects become dominant. The universe begins to look different. Clocks no longer agree in the ordinary way. Distances no longer appear the same to every observer, and every additional increase in speed demands more energy than the increase before it. Imagine a spacecraft beginning far from Earth. Its engines activate gently. At first, the craft gains speed in a familiar way. A little more energy produces a little more motion. The spacecraft reaches 10% of light speed, then 20%, then half the speed of light. At each stage, the energy requirement grows. As it moves closer to light speed, the relationship becomes increasingly severe. Reaching 90% of light speed requires enormous energy. Reaching 99% requires far more. Reaching 99.9% requires more again. Each additional 9 after the decimal point becomes increasingly expensive. The speed increases by a smaller amount. The energy requirement rises dramatically. At exactly the speed of light, the required energy would become infinite. A physical spacecraft cannot supply infinite energy. It cannot store it. Its engines cannot produce it. Its structure cannot contain it. The light speed boundary is therefore not simply an engineering challenge. It is built into the known structure of space-time. A ship cannot overcome it by constructing a stronger engine in the ordinary sense. Even a perfectly efficient engine would still face the same mathematical limit. The faster the spacecraft travels, the harder it becomes to increase its speed further. Light itself does not encounter this problem because photons have no rest mass. They always move at light speed in a vacuum. A spacecraft contains matter, its structure, fuel, passengers, computers, shielding, Every massive component remains below the limit. Yet relativity offers something that initially sounds like a way around the problem: time dilation. For a traveler moving close to light speed, less time may pass than for observers who remain behind. A journey lasting thousands of years according to Earth may feel much shorter aboard the spacecraft. This does not allow faster-than-light travel. The ship still moves below the speed of light, but the traveler's experience of the journey changes. Suppose a spacecraft travels toward a star 10 light-years away. At a speed very close to light, Earth observers see the journey lasting a little more than 10 years. The travelers may experience fewer years. At even greater speeds, they may experience much less. Their clocks run normally from their own perspective. Their hearts beat normally. Their thoughts continue normally. Nothing aboard feels slowed. But when their clocks are compared with clocks on Earth, less time has passed for them. This effect has been measured. Fast-moving particles survive longer in laboratories than they would at rest. Atomic clocks carried on aircraft and satellites accumulate small but detectable differences. Navigation systems must account for relativistic effects to remain accurate. Time dilation is not a visual illusion. It is a physical feature of space-time. Near light speed, it could become enormous. A traveler might cross a great interstellar distance while aging only a fraction of the time measured on Earth. This creates the possibility of reaching faraway stars within one traveler's lifetime, at least in principle. But the cost remains extraordinary. The spacecraft must accelerate to the required speed. It must survive the journey. Then it must slow down near the destination. Every stage requires energy, and every collision with dust or gas becomes dangerous at relativistic speed. A tiny grain of matter, moving slowly within the galaxy, would strike the spacecraft with tremendous energy. From the ship's perspective, the grain approaches at almost light speed. A particle smaller than a grain of sand could release energy comparable to a powerful explosion. Hydrogen atoms become a stream of high-energy radiation. Dust becomes a serious hazard. The emptiness between stars is not perfectly empty. It contains thin gas, dust, cosmic rays, magnetic fields, occasional larger objects. At ordinary spacecraft speeds, most of this material presents only a manageable challenge. Near light speed, the energy of impact rises dramatically. The spacecraft would require advanced shielding, perhaps layers designed to absorb particles, magnetic or electric fields to redirect charged matter, a protective cloud released ahead of the craft, or a system capable of detecting and destroying larger grains before impact. The shield itself adds mass. More mass requires more energy to accelerate. More fuel adds more mass again. The engineering problem grows recursively. The ship must carry what protects it, then carry the energy needed to accelerate that protection, then perhaps carry the systems needed to control the energy source. A realistic relativistic craft would likely need to be extremely efficient and carefully designed. Even then, reaching another galaxy would remain far beyond an ordinary interstellar journey. The nearest major galaxy lies millions of light-years away. At almost light speed, Earth would still measure millions of years passing. The travelers might experience far less because of time dilation, but the galaxy they left would evolve dramatically. Stars would be born and die. Civilizations could rise and disappear. The travelers might arrive after an immense span of external history. A return journey would deepen the separation. They might experience years or decades. Earth could experience millions. The home they remember would no longer exist in any familiar form. Relativistic travel changes the meaning of departure. The traveler does not merely cross distance. The traveler moves into the future of the universe. This effect becomes more extreme as the destination grows farther away. A craft traveling toward the edge of the observable universe might experience a compressed journey if it could accelerate close enough to light speed. But Earth would see the trip taking tens of billions of years or more. The universe would not remain unchanged during that time. Cosmic expansion would continue. Distant galaxies would move. Stars would evolve. The target itself might cross beyond the craft's reachable horizon. Time dilation reduces the traveler's experienced time. It does not freeze cosmic history. It does not stop expansion. It does not guarantee that the destination remains accessible. This distinction is essential. Relativity can make a long route feel shorter to the traveler. It cannot allow the spacecraft to outrun a causal boundary. The ship still moves through local space below light speed. If expanding space carries a destination away too quickly, the craft may never close the gap. The horizon is not defeated because the traveler's clock runs differently. A horizon describes whether any path through space-time can connect two events. If no light signal sent now can reach a region, no slower spacecraft can reach it either. The problem is geometric, not psychological, not merely a matter of patience. Consider a distant galaxy whose ancient light reaches Earth today. The photons began traveling billions of years ago. During that time, the universe expanded. The galaxy's present distance increased enormously. A spacecraft leaving now starts later than those photons did. It enters a universe that has already expanded for billions of additional years. The route available to the old light may no longer be available to the new traveler. The ship cannot simply follow the same path. The path existed within an earlier cosmic geometry. This is similar to trying to cross a bridge after part of it has been carried away by a growing river. The earlier traveler crossed while the route remained connected. The later traveler finds the separation increasing too quickly. Relativistic speed helps only while a causal path still exists. Even within reachable space, acceleration introduces another challenge. A human body cannot instantly jump to near light speed. Sudden acceleration would be destructive. A comfortable spacecraft might accelerate at a rate similar to Earth's gravity. Passengers would feel a steady pressure beneath their feet. The ship could rotate or accelerate continuously to provide a gravity-like environment. At one Earth gravity, the craft would gain speed gradually. After roughly 1 year of onboard acceleration, it would already be moving at a substantial fraction of light speed relative to Earth. Continued acceleration would bring it increasingly close to the limit. The craft would never cross light speed, but the travelers would experience a continuous force resembling weight. Halfway to the destination, the spacecraft might turn around. Its engines would then fire in the opposite direction. The second half of the journey would be spent slowing down. This imagined travel profile is sometimes used to explore relativistic voyages. It creates remarkable results. From the traveler's perspective, extremely distant places could be reached within a human lifetime if continuous acceleration and energy requirements were ignored. A journey across the observable universe might feel surprisingly short compared with the time measured from Earth. The reason is not that the craft travels faster than light. The distance along the traveler's frame becomes length contracted. At high relative speed, the space ahead appears compressed in the direction of motion. Time dilation and length contraction are different descriptions of the same relativistic geometry. Earth observers describe the traveler's clock as slow. The traveler describes the distance as shortened. Neither description is more real than the other. Both are consistent within their own frames. This may seem like a path to the cosmic edge. Accelerate long enough, allow the distance to contract, cross billions of light years within a lifetime. But the simplified calculation usually assumes a static or idealized universe. The real universe expands. Its distant regions are separated by changing geometry. The observable horizon is not a stationary target, and continuous acceleration for billions of light years demands an energy source beyond anything currently imaginable. The ship would also need to survive radiation that becomes increasingly intense in its forward direction. As speed increases, ordinary background light is shifted toward higher energy. Visible light may become ultraviolet. Infrared may become visible. Microwaves may become energetic radiation. The cosmic microwave background, normally a faint microwave glow, would be blue shifted ahead of the spacecraft. At extreme speeds, it could become a dangerous beam of high-energy radiation. The universe in front of the ship would appear concentrated. Light would be aberrated toward the direction of motion. Stars that normally surround the craft would seem crowded into a smaller region ahead. Behind, light would be redshifted and weakened. The view would no longer resemble an ordinary star field. The traveler would see a universe distorted by motion. The forward sky would brighten and shift in color. Radiation protection would become essential. The faster the ship moves, the more severe the effect. At sufficiently extreme speeds, even low-energy photons become hazardous. The craft would not travel through quiet darkness. It would travel into an increasingly energetic wall of light and particles. This creates another practical limit below light speed. The equations may permit a speed. The environment may not. A spacecraft requires matter capable of surviving heat, radiation, and impact. It requires systems capable of repairing damage for long periods. It requires an energy supply capable of continuous acceleration. It requires a way to remove waste heat. Every engine produces heat. Every computer, every life support system. In space, heat cannot be carried away by surrounding air. It must be radiated. Radiators require surface area. Large surfaces may be vulnerable to impact. The faster the craft moves, the more difficult the balance becomes. An advanced civilization might use an external energy beam. A powerful laser could push a light sail. The spacecraft would not need to carry all its fuel during acceleration. This reduces mass. Small probes might reach a significant fraction of light speed using such a method. But a beam becomes difficult to focus across enormous distances. The sail must remain aligned. Slowing down at the destination requires another method. A second beam may not be waiting there. The craft could use magnetic sails interacting with interstellar particles, or use the target star's light, or carry fuel for deceleration. Each solution introduces new complications. Another possibility is antimatter. Matter and antimatter can convert much of their mass into energy when they meet. This makes antimatter an extremely dense fuel in principle, but producing large quantities is extraordinarily difficult. Storing it safely is harder still. Antimatter cannot touch ordinary matter without annihilating. It must be held through electromagnetic fields. A failure could release enormous energy. Even with antimatter, the spacecraft does not escape relativity. The energy source may become better. The infinite barrier remains. Fusion is another possibility. Stars release energy through fusion. A spacecraft might fuse light elements and direct the products backward. Fusion fuel could support high-speed travel more effectively than chemical rockets. Yet known concepts still fall far below light speed for large crewed vehicles. Interstellar travel may be possible eventually. Travel across billions of light years is a different scale entirely. The problem is often hidden by percentages. 10% of light speed sounds close to light speed. It is extremely fast compared with current spacecraft. But crossing 1 million light years at that speed still requires 10 million years from the external perspective. Crossing 46 billion light years would require hundreds of billions of years in a static universe. The universe is not static. By then, cosmic conditions would be radically different. Even 99% of light speed leaves enormous travel times across cosmological distance. The difference between fast and almost light speed matters greatly for interstellar travel. Across the observable universe, even almost is not enough in the ordinary frame. Only extreme time dilation makes the traveler's experience shorter. But the external universe continues aging. This produces one of relativity's most peaceful and strange consequences. A traveler could leave a young universe and arrive in an ancient one. Perhaps the ship experiences 50 years. Outside, billions pass. Stars fade, galaxies merge, black holes grow. The cosmic microwave background cools further. The destination may not resemble the image observed before departure. The telescope showed ancient light. The journey ends in a far later era. The traveler never reaches the galaxy as it appeared in the photograph. That version existed billions of years before departure. It is already gone. Every journey through space is also a journey through time. Even a trip to the moon ends slightly later. Across cosmological distances, this becomes overwhelming. The target observed from Earth is not a current place waiting unchanged. It is a historical image. A spacecraft heads toward where the source will be, not where it was when its light began the journey. Astronomers must predict motion, expansion, gravitational interactions, stellar evolution. Across billions of years, tiny uncertainties grow. A civilization could aim toward a galaxy and arrive after it has merged with another, or after its stars have changed. The destination becomes a future region rather than the object seen. This makes the phrase "travel to the edge we can see" misleading. The edge we see belongs to the past. The arrival would belong to an unimaginably distant future. The two cannot coincide. A spacecraft cannot catch an ancient image. It can only travel toward the later continuation of the place that produced it. Cosmology therefore separates seeing from visiting in another way. Observation receives old information. Travel reaches future conditions. The greater the distance, the wider the separation. For the nearest stars, a few years divide image and arrival. For distant galaxies, millions or billions. Near the cosmic horizon, the difference spans much of cosmic history. Another complication arises from communication with the spacecraft. A mission traveling near light speed quickly becomes separated from Earth by long signal delays. Messages sent from the craft move at light speed. Earth receives them years or millennia later. Instructions sent from Earth may never catch the ship if it is moving away at nearly light speed. The mission must become independent. It cannot rely upon continuous guidance. Its systems must navigate, repair, make scientific decisions, adapt to unexpected conditions. A crewed mission would need a self-sufficient civilization aboard, or an automated intelligence capable of functioning for immense periods. The ship would become more like a traveling world than a vehicle. Generations might live and die aboard it if the experienced journey remained long. At extreme relativistic speed, time dilation could reduce the onboard duration, but acceleration, shielding, and energy remain. If the craft ever returns, its home world may be unrecognizable. The travelers become visitors from the distant past. This is sometimes called the twin effect. One traveler leaves at high speed, the other remains. When they meet again, the traveler has aged less. The difference is not because one clock malfunctioned. The travelers followed different paths through space-time. Across a cosmological voyage, the age difference could become immense. The spacecraft might preserve people, language, and technology from an era forgotten by the destination civilization. A journey toward the cosmic horizon may therefore be one-way culturally, even if the craft can reverse course physically. The home history moves beyond reach. The traveler cannot return to the same world they left because that world no longer exists in time. Space travel at relativistic speed is also time travel toward the future. There is no known way to reverse the effect and return to the past. The ship can slow down, turn around, come home, but home's clock has continued. The lost years cannot be recovered. This makes extreme travel less like exploration followed by return, more like migration into a future. A civilization sending such missions would need to accept permanent separation. Perhaps only machines would travel. Machines can survive long intervals more easily than biological bodies. They can become dormant, repair themselves, transmit data. A small probe requires less energy than a city-sized ship. It may reach higher speed. Yet even a probe cannot cross a true event horizon in the wrong direction. It cannot reach regions outside its causal future. It cannot send information back from places whose signals can never return. A probe may travel farther than humanity can influence directly, but eventually, it too encounters the structure of cosmic expansion. If it crosses a horizon relative to Earth, communication ends permanently. The probe may continue existing, observing, traveling, but Earth will never receive its later data. From the probe's perspective, the mission continues. From Earth's perspective, it becomes silent. This is an important distinction. A journey can continue beyond communication. The spacecraft does not disappear physically at the horizon. It becomes causally separated. No later signal can bridge the expanding distance. Earth receives the final transmissions, increasingly delayed and redshifted. Then nothing further. The craft passes out of our possible history. This resembles an object approaching a black hole's event horizon from a distant observer's perspective, though the cosmological situation is not identical. In both cases, a horizon separates regions of possible communication. Crossing does not necessarily produce a local war. The traveler may notice nothing dramatic at the exact boundary, but the relationship with the distant observer changes permanently. No return signal arrives. A cosmic horizon is therefore not something a traveler crashes into. It is a boundary in the structure of cause and effect, a line separating events that can influence one another from events that cannot. This makes it more fundamental than a distant barrier. A wall can be broken. A horizon cannot be crossed in the forbidden causal direction using ordinary sublight motion. No stronger hull changes that. No additional fuel changes it. The limitation belongs to space-time itself. Relativity, then, offers both possibility and restraint. It allows travelers to experience shorter journeys. It allows different observers to measure different times and distances. It creates the possibility of reaching faraway stars while aging slowly, but it preserves the light speed limit. It does not make the observable edge reachable. It does not stop expansion. It does not allow information to escape every horizon. The universe remains consistent. The same geometry that shortens the traveler's experienced route also defines which routes exist at all. Near light speed, the traveler can cross remarkable distances, but not every distance, not every destination, not every future. The edge of the observable universe remains a boundary of information, moving with time and perspective. A spacecraft may chase it indefinitely, As the craft advances, a new observable horizon forms around its own location. The horizon does not wait ahead like a finish line. The traveler carries a new window through the universe. Regions once invisible may become observable. Other regions fall outside view. No final shell is reached. The universe is not peeled open to reveal an exterior. Instead, the traveler moves from one limited perspective to another. This may be the central lesson of relativistic exploration. Motion changes the window. It does not remove the fact that every observer has a window. No location provides access to all cosmic information. Even an advanced civilization spread across many galaxies would possess only a collection of overlapping horizons. Each outpost would see part of the whole. Signals between them would take immense time. Expansion could eventually separate them. A cosmic civilization might grow across reachable space and still never touch the entire universe. Its knowledge would remain local in the deepest sense. Not small, but bounded by causality. This does not make exploration meaningless. A journey to another star would reveal worlds inaccessible from Earth. A journey across the Milky Way would encounter regions of enormous variety. Different stars, nebulae, black holes, planetary systems, perhaps life. There is more accessible possibility within one galaxy than any single civilization may ever exhaust. The unreachable edge is not a reason to stop moving. It is a reminder that the universe does not need to be fully reachable to be understood more deeply. For now, the imagined spacecraft continues accelerating. Its engines glow behind it. Earth becomes a faint point. The sun joins the surrounding stars. Time aboard passes steadily. Outside, years begin stretching into centuries. The forward sky gathers into a bright, compressed region. Background radiation shifts toward higher energies. The craft approaches light speed without ever reaching it. Ahead lies a distant galaxy. But beyond that galaxy, space continues. More clusters, more cosmic web, more horizon. The traveler may cross distances once considered impossible. Still, there is no final wall, no fixed edge waiting to be touched. Only deeper regions of space-time and new limits of communication. The next part of this journey will explore the energy required for such travel, why even tiny amounts of matter become dangerous near light speed, and whether speculative ideas such as warp drives or wormholes could offer a path beyond the ordinary relativistic limit. Speed is only one part of the journey. Energy is the other. A spacecraft does not become difficult to accelerate merely because light speed is far away. It becomes difficult because every increase in velocity must be paid for with energy. At ordinary speeds, this cost behaves in a familiar way. A vehicle moves faster when its engine supplies more power. A rocket burns fuel. The exhaust moves backward. The spacecraft gains momentum in the opposite direction. But near the speed of light, the energy requirement rises far more sharply than everyday intuition expects. A small probe accelerated to 10% of light speed would already carry an extraordinary amount of kinetic energy. A large crewed spacecraft would require vastly more, and the vehicle would need additional energy to slow down after arrival. A journey is not complete when the ship passes the destination at enormous speed. It must enter orbit, approach a planet, or remain near the region it intends to study. Acceleration is only half of the problem. Deceleration is the other half. The ship may need to spend almost as much energy slowing down as it spent gaining speed. This is one reason interstellar travel concepts often favor small probes. A gram-scale craft needs far less energy than a vessel containing people, life support systems, shielding, food, water, engines, and repair equipment. Even a tiny probe could perform useful science. It could photograph another planetary system, measure magnetic fields, search for atmospheres, transmit observations home, but a tiny probe traveling at a significant fraction of light speed would still require an enormous launch system. The energy may not be carried aboard. A laser array near Earth could illuminate a reflective sail. Photons possess momentum. When they strike the sail, they push it. The force is small, but a powerful beam maintained over time could accelerate a very light spacecraft to remarkable speed. The sail would need to be thin, reflective, and stable under intense illumination. The beam would need extraordinary precision. As the probe moved farther away, keeping the laser focused upon it would become increasingly difficult. Even slight pointing errors could cause the beam to miss. The sail might need to adjust its orientation continuously. The probe would need to survive vibration, heating, and acceleration. Yet the concept has one important advantage. The craft does not carry the energy source. The heavy machinery remains near Earth. Only the probe and sail are accelerated. This improves efficiency. But the same system does not automatically provide a way to slow down at the destination. The target star may offer light pressure. Magnetic fields may help. A magnetic sail could interact with charged particles. Or the probe could fly through the system quickly, collecting observations during a brief passage. A flyby may be enough for the first interstellar mission. A journey toward the edge of the universe demands much more. There would be no prepared laser array waiting near every galaxy. No convenient destination infrastructure. No simple way to maintain acceleration over billions of light years. The energy system would need to travel with the spacecraft, or be distributed along the route. A civilization might build stations between stars. Each station could accelerate passing craft. Then another station farther ahead could continue the process. This would create an interstellar transportation network. Within one galaxy, such infrastructure may be imaginable for a civilization operating across immense time. But between galaxies, the distances become much larger, matter becomes thinner, construction becomes harder, and cosmic expansion continues changing the route. The network would need to grow faster than distant regions recede. Eventually, horizons would prevent further connection. Even unlimited engineering cannot build a station in a region no signal can ever reach. Energy also creates a problem of heat. An engine does not convert energy into motion perfectly. Some becomes waste heat. Computers create heat. Life support systems create heat. Protective shields absorb radiation and particles. In space, there is no surrounding air to carry this energy away. A spacecraft must radiate it as light, usually infrared light. Large radiators can release heat efficiently, but radiators add surface area and mass. At relativistic speeds, broad structures may be exposed to impacts. A radiator must remain both large and protected. This creates another design tension. The ship needs surface area to cool, yet it benefits from a narrow shape facing forward. Perhaps radiators could extend sideways. Perhaps they could operate behind protective fields. Perhaps heat could be stored temporarily during the fastest stage of travel. But a journey lasting years, centuries, or longer requires a continuous solution. Energy that enters the spacecraft must eventually leave. No material can absorb heat forever. The faster the ship moves, the more energy arrives from the environment ahead. Interstellar space contains hydrogen atoms, helium, dust, cosmic rays. Each one appears more energetic from the perspective of the spacecraft. The ship may use a forward shield, a thick layer of material designed to erode slowly, or several separated layers. The first layer breaks particles apart. Later layers absorb the fragments. A magnetic field could redirect charged particles. Neutral atoms and dust would be harder. Powerful lasers might detect and vaporize larger grains before impact. But the warning time would be extremely short. At half the speed of light, the spacecraft crosses 150,000 kilometers every second. A particle detected 1,000 kilometers ahead arrives in only a few thousandths of a second. Automated systems would need to react almost instantly. At even higher speed, the available time becomes shorter. The probe may release a thin cloud ahead of itself. The cloud encounters dust first. Its particles disperse the impact energy before the debris reaches the main craft. The vehicle travels inside a moving protective region, but the cloud must be replenished. Its particles spread naturally. More material adds mass. Every protective solution affects the energy budget. The ship must accelerate, not only passengers and instruments. It must accelerate shielding, fuel, radiators, spare parts, and perhaps material sacrificed intentionally during the journey. This is why relativistic travel favors minimal mass. Every kilogram becomes expensive. A large vessel may require energy comparable to the long-term output of a civilization. A journey to the observable horizon would demand far more. And no matter how much energy is supplied, the light speed limit remains. This leads naturally to speculative ideas. Instead of pushing a spacecraft through space faster and faster, perhaps space itself could be changed. One famous concept is the warp drive. The idea does not require the craft to move locally faster than light. Instead, space-time would contract ahead of the vessel and expand behind it. The ship would remain inside a region sometimes described as a warp bubble. Within the bubble, The craft may be nearly at rest relative to nearby space. The bubble itself would carry the craft across a larger distance. This is attractive because cosmic expansion already demonstrates that distances can increase faster than light without objects locally breaking the speed limit. Perhaps in principle, engineered space-time could do something similar. But turning the mathematical idea into a physical engine is profoundly difficult. The original warp drive solution requires unusual forms of energy, often described as negative energy density. This does not simply mean energy with a minus sign on an ordinary fuel gauge. It refers to a physical condition unlike the normal matter and radiation available in large quantities. Quantum physics allows limited situations in which energy density can appear lower than a surrounding reference state. But producing, controlling, and maintaining the enormous space-time distortions required for a useful warp bubble remains far beyond known engineering. Some later theoretical studies have explored alternative geometries. A few reduce particular difficulties, others replace them with different ones. The energy demand may remain immense, the bubble may be unstable, creating it from inside could be impossible, controlling its direction may be difficult. The front of the bubble may become causally separated from the spacecraft, meaning the travelers cannot easily steer or stop it using ordinary internal signals. Radiation could accumulate around the bubble. When the field collapses, that stored energy might be released. The mathematics does not automatically provide a safe transportation system. It provides a possible geometry under carefully defined assumptions. This difference is essential. Physics can describe many space-time shapes. Not every shape can be constructed from realistic matter. A bridge may be drawn in equations. The universe may not provide the material required to build it. A warp drive would also need to address cosmic horizons. Even if a bubble crossed local space effectively faster than light, could it enter a region outside every causal connection? The answer depends upon the full theory and remains uncertain. Many warp concepts risk violating causality. If information can travel faster than light in one frame, another frame may describe it as arriving before it was sent. This opens the possibility of closed loops in time. A message might return to its own past. Known physics strongly resists such outcomes, though a complete theory of quantum gravity does not yet exist. A practical warp drive may require solving not only energy and stability, but the deeper relationship between faster-than-light travel and causality. Wormholes offer another speculative possibility. A wormhole is imagined as a shortcut through space-time. Two distant regions are connected by a tunnel. The traveler does not cross the ordinary distance between them. It enters one mouth and exits another. A journey that would normally require millions of years might take minutes. The analogy of a folded sheet of paper is often used. 2 points far apart on the surface are brought close together by folding the sheet. A tunnel passes directly between them. The traveler crosses the shorter internal path. General relativity allows mathematical solutions resembling wormholes. But the simplest examples collapse too quickly for passage. A traversable wormhole would likely require exotic conditions to hold it open. Once again, negative energy appears. The wormhole may also be unstable when matter enters. Quantum effects could become extreme near the throat. Even if stable wormholes existed naturally, finding one would be difficult. The mouths might resemble compact gravitational objects. They could be surrounded by intense radiation. Their destinations would not necessarily be useful. One may open near another galaxy, or inside an empty region, or near a destructive environment. And a wormhole does not automatically solve the first construction problem. If both mouths must be created together and then moved apart below light speed, the shortcut cannot connect a region that no earlier process reached. One mouth would need to be transported to the distant destination. That journey still faces the original limit. Once established, the wormhole could shorten later travel, but it cannot easily build a path to a region already beyond every possible signal. A naturally existing wormhole might be different. Its two mouths could connect distant locations without human construction. Discovering one would transform travel. Yet there is no observational evidence that traversable wormholes exist. Black holes are sometimes imagined as gateways, but an ordinary black hole is not known to offer a safe route elsewhere. Its event horizon allows entry, not return. Inside, known general relativity leads toward regions of extreme curvature. Some mathematical solutions contain bridges to other regions of space-time, but these bridges are not stable passages for travelers. The internal geometry changes too quickly, the path closes, and realistic black holes formed from collapsing stars do not provide the idealized structure seen in simplified equations. A traveler entering a black hole would not emerge conveniently near the edge of the universe. The event horizon is a boundary of communication. No signal sent from inside can return to the exterior. The black hole is therefore more like a one-way causal region than a portal available for navigation. Rotating black holes produce even more complicated mathematical interiors. But small disturbances may make those structures unstable. Quantum gravity may change the final picture. Present knowledge does not support black hole travel as a practical route. Another speculative idea involves cosmic strings. These are hypothetical defects that may have formed during phase transitions in the early universe. They would be extremely thin, but carry enormous mass and tension. Certain arrangements of moving cosmic strings have been studied as possible ways to create unusual paths through space-time. In some mathematical scenarios, a traveler could return to an earlier time or take a shortcut, but no cosmic string has been confirmed. The required configurations may be unrealistic, and once again, causality problems appear. The more effectively an idea seems to bypass light speed, the more likely it is to create time-ordering difficulties. Nature may contain a deeper principle that protects causality. Perhaps every faster-than-light geometry is prevented by instability. Perhaps quantum effects destroy the shortcut before it becomes usable. This possibility is sometimes described broadly as chronology protection. The exact mechanism remains unknown. Still, the repeated appearance of paradoxes suggests that faster-than-light travel may not be merely difficult. It may be incompatible with the way cause and effect are organized. Suppose a spacecraft could send a message to a distant observer faster than light. Because observers moving relative to one another divide time differently, some frame may describe the message as arriving before its transmission. A reply sent through another faster-than-light route might return before the first message was created. The sender could receive an answer to a question not yet asked. The result would threaten the ordinary sequence of cause and effect. Physics may forbid the required conditions before the paradox forms. Warp bubbles may collapse, wormholes may destabilize, negative energy may be restricted by quantum inequalities. A complete theory may show that usable shortcuts cannot exist. Or perhaps the universe allows them under conditions not yet understood. At present, no experiment demonstrates a method for sending matter or information faster than light. Speculation remains valuable because it tests the limits of theory. A warp drive equation helps physicists examine how energy shapes space-time. Wormholes help explore geometry, gravity, and quantum information. Even if no spacecraft ever uses them, the ideas reveal connections between relativity and the deeper structure of the universe. Some modern research links wormhole-like mathematics with quantum entanglement. Two particles can share correlations that remain connected across distance, but entanglement does not allow ordinary information to be transmitted faster than light. The measurement results appear individually random. Only after the observers compare their data through normal slower-than-light communication do the correlations become visible. Quantum mechanics behaves strangely. It still preserves the causal limit in every confirmed experiment. Teleportation is another word that creates confusion. Quantum teleportation transfers the quantum state of a system using entanglement and ordinary communication. It does not move a person instantly. It does not send usable information faster than light. The original state is not copied freely. The procedure requires classical data to be transmitted normally. A large object contains an unimaginable number of quantum details. Reconstructing a living body atom by atom would exceed any current capability. Even if possible, profound questions about identity would remain. Would the reconstructed person be the traveler or a copy? The original arrangement may need to be destroyed during the process. The method would not create a simple vehicle toward the edge of the universe. It would still require an entangled system or receiving apparatus at the destination. That apparatus must arrive somehow. The same first path problem returns. Many shortcuts require the destination to be prepared in advance. A gate, a wormhole mouth, an entangled receiver, a beacon. Infrastructure cannot be installed in a region that cannot be reached. This is one reason the cosmic horizon remains so powerful. It limits not only ordinary travel, it limits preparation. A civilization cannot build a bridge endpoint beyond the region it can influence. Perhaps unknown physics changes this conclusion. A complete theory of quantum gravity may reveal new possibilities. Current theories are incomplete near singularities, and at the smallest scales, dark energy is not fully understood. Most of the universe's matter appears to be dark matter, whose particle nature remains unknown. There is much that physics has not yet explained. But unknown physics is not automatically permission for any imagined technology. A new theory must reproduce the successful predictions of relativity and quantum mechanics. It must remain consistent with experiments. It may introduce new routes or strengthen existing limits. Scientific openness includes both possibilities. A future discovery may show that space-time can be engineered. Another may reveal why it cannot. For now, the most reliable rule remains local light speed travel. Signals move at or below light speed. Matter remains below it. Distances between remote regions change through expansion. Horizons separate causal futures. Within these limits, remarkable journeys may still be possible. A civilization could send probes toward nearby stars. Then farther across its galaxy, it could build self-repairing vessels, use laser sails, fusion, antimatter, artificial intelligence, generational habitats. It might spread gradually through the Milky Way over millions of years. A million years is enormous compared with human history, but small compared with the age of the galaxy. An interstellar civilization does not need faster-than-light travel to explore widely. Patience can replace speed. Each settled system launches craft toward the next. Expansion proceeds like a slow wave through the galaxy. The civilization never sends one ship across 100,000 light-years. It sends many ships across a few light-years at a time. Infrastructure grows locally. Information remains delayed. Cultures may separate. But physical expansion through one gravitationally bound galaxy remains possible in principle. Crossing to nearby galaxies may also remain possible over far longer periods. The local group is gravitationally bound. The Milky Way, Andromeda, and many smaller galaxies share one large region. Cosmic expansion does not pull them apart permanently. Over time, several will merge. A civilization lasting long enough could explore much of this local domain without fighting accelerated expansion between its members. Beyond the local group, the picture changes. Most distant galaxy groups are not gravitationally bound to us. Dark energy carries them away. Even a civilization with near-light speed spacecraft must begin early enough to reach them. As cosmic time passes, the accessible territory shrinks. Future travelers will have fewer external galaxies available. Some destinations that can still be reached today will eventually cross beyond the horizon. The universe is therefore not only large, it is time-sensitive. A route open now may close later. This does not happen over human lifetimes for nearby galaxies. The timescales are vast, but cosmologically, the opportunity is temporary. No spacecraft can wait forever and still reach every currently reachable region. The expanding universe creates a deadline written across billions of years. A sufficiently long-lived civilization might notice. It may send probes outward before regions disappear, not because of urgency in the human sense, because causality slowly changes. The probes may never send information home after crossing certain boundaries, yet they could carry archives, life, machines, seeds of civilization. The expansion would become one way, a chain of descendants moving beyond communication. Each carries the history of earlier worlds. Eventually, distant branches become separate universes in practical terms. They share an origin, no longer a future conversation. This is one way a civilization could approach the limits of reach without violating physics. Not one ship racing to the edge. A network spreading while connection remains possible. The frontier moves outward. Behind it, regions become causally isolated. No central civilization experiences the whole. The expansion is distributed across time and space. Even then, the observable edge remains beyond reach. Every outpost has its own horizon. The network cannot cover an infinite universe. It cannot enter regions that expansion permanently separates. It can only occupy part of the space-time available from its origin. Perhaps this is the deepest energy lesson. The challenge is not producing one impossibly powerful engine. It is recognizing that no amount of power grants access to every location. Energy can accelerate matter, shield a spacecraft, build stations, curve space-time slightly. but causality determines which destinations belong to the future at all. A civilization may become immensely powerful while remaining inside one finite region of possible influence. Power does not erase geometry. For now, imagine the relativistic spacecraft moving through the dark. Its forward shield absorbs a thin rain of particles. Radiators glow faintly behind it. The engine converts stored matter into energy with remarkable efficiency. The ship has crossed several light years. Its speed is beyond anything built by present humanity. Yet the next galaxy remains millions of light years away. The cosmic horizon lies farther still. The travelers examine theoretical maps, warp bubbles, wormholes, quantum links. Each offers a beautiful idea. None provides a verified path. The craft continues according to the physics known to work. Below light speed, through ordinary space-time, the journey remains extraordinary without becoming impossible in every detail. Nearby stars can still be reached in principle. The galaxy can still be explored slowly. The universe does not need to surrender all of its distances for exploration to matter. The next part of this journey will examine cosmic expansion more closely, exploring why distant galaxies can recede faster than light, how dark energy changes the future, and why much of the universe visible tonight is already beyond any journey humanity could begin now. The universe does not expand like an explosion moving into empty space. There is no known central point from which every galaxy was launched. There is no visible outer region waiting to be filled. Instead, the distances between widely separated, gravitationally unbound regions increase with time. Space itself changes scale. This is difficult to picture because ordinary objects do not behave this way. A room does not grow while people stand inside it. A road does not lengthen continuously beneath a moving car. But across the largest cosmic distances, the geometry between galaxies evolves. Imagine many small dots drawn across the surface of a flexible balloon. As the balloon inflates, every dot becomes farther from every other dot. No dot sits at the center of the two-dimensional surface. From the viewpoint of any dot, the others appear to move away. The analogy is incomplete. The universe is not known to be the surface of a balloon inside a larger room, but it helps illustrate how expansion can occur without one preferred center. Every distant galaxy sees a broadly similar pattern. Nearby galaxies may move toward one another because gravity dominates locally. Farther away, the overall expansion becomes clearer. The more space lies between two unbound galaxies, the faster their distance tends to increase. This relationship is described by the Hubble expansion. A galaxy twice as distant generally recedes approximately twice as rapidly through the large-scale cosmic flow. A galaxy 10 times farther away is carried away more quickly still. This does not mean every galaxy moves perfectly with the expansion. Galaxies have local motions. They orbit within groups, pass near neighbors, fall toward clusters, collide. The Milky Way and Andromeda are moving toward one another, despite the expansion of the wider universe. Gravity binds them within the local group. Their approaching motion is not evidence that expansion has stopped. It means local gravity is stronger than cosmic expansion at that scale. The same is true within the solar system. Expansion does not stretch Earth away from the Sun. Gravity holds the orbit together. It does not expand atoms or human bodies. Electromagnetic forces bind matter far more strongly. Cosmic expansion dominates only where the average density becomes low enough and the distances become immense. The spaces between major galaxy groups are where the effect appears most clearly. Across those voids, matter is too thinly distributed to remain bound as one system. The distance grows. As the distance grows, more expanding space lies between the regions. The separation rate becomes greater. Eventually, it can exceed the speed of light. This sounds impossible only if recession is imagined as ordinary motion through static space. A nearby observer beside one of those distant galaxies would not see it speeding past local space faster than light. Locally, physics behaves normally. The galaxy's nearby stars remain below light speed. Its planets orbit normally. Light still passes every local observer at the same measured speed. The faster-than-light value describes the change in an enormous total distance across expanding spacetime. Relativity limits local motion. It does not require the global distance between remote regions to increase below light speed. This distinction allows ancient light from a galaxy to reach Earth even when that galaxy is now receding faster than light. The light may have begun its journey when the galaxy was much closer, At first, expanding space may have carried the photon away from Earth, despite the photon moving locally toward us. The distance between the photon and Earth could still increase, but the expansion rate changed during the journey. Eventually, the photon entered regions where the recession was slower. Then it began making progress. After billions of years, it arrived. The path was not a simple race across fixed space. It was movement through a changing cosmic geometry. The light reaching our telescopes tonight may therefore come from places now separated from us at a superluminal rate. Their past remains visible. Their future may not be reachable. This creates two very different cosmic boundaries. One describes what can be observed now. The other describes what can ever be influenced from now onward. The observable universe extends about 46 billion light-years in every direction, when present distance is considered. But the region that a signal sent from Earth today can ever reach is far smaller. The exact values depend upon the cosmological model. Under the standard picture of an accelerating universe, a signal leaving Earth now can eventually reach objects currently located only within roughly 16 billion light-years of us. Beyond that approximate boundary, expansion prevents the signal from ever arriving. This boundary is known as the cosmic event horizon. It is not a bright shell. No marker exists there. A spacecraft crossing the relevant distance would not strike anything. The horizon is defined by the future paths available through space-time. A region beyond it cannot be influenced by an event occurring here now. No radio message, no laser pulse, no spacecraft. Even light cannot complete the journey. Many galaxies currently visible lie beyond this future contact boundary. We observe them because their old light departed when the universe was smaller, but a reply sent today would never reach them. The relationship is one way across time. They have already sent information toward us, although not deliberately. Their starlight crossed the universe. We receive it, but the present versions of those galaxies have moved outside our causal future. A civilization living there today could transmit toward Earth and still fail to reach us, depending upon its current position and the expansion between us. Two civilizations might observe one another's ancient planets while being unable to exchange a single new message. Each sees a version of the other from a time when contact was still geometrically possible. By the time intelligence develops and responds, the route has closed. The universe can preserve visibility after communication has become impossible. This is one of the most subtle forms of cosmic isolation. Distance alone does not cause it. Expansion combined with time does. Why is the expansion accelerating? Modern cosmology uses the term dark energy to describe the component associated with this behavior. The name reflects uncertainty rather than detailed understanding. Dark energy does not mean dark matter. Dark matter behaves gravitationally like additional unseen mass. It helps hold galaxies and galaxy clusters together. Dark energy has the opposite large-scale effect. Observations of distant stellar explosions, the cosmic microwave background, and the distribution of galaxies support a universe in which this component dominates the current large-scale energy budget. The simplest model treats dark energy as a constant property of empty space. This is often connected with the cosmological constant in Einstein's equations. If the amount of dark energy per unit volume remains constant while space expands, then the total influence of dark energy grows as more space appears. Ordinary matter becomes more diluted. Radiation becomes weaker. But the density associated with the cosmological constant remains unchanged. Over time, accelerated expansion becomes increasingly dominant. The exact nature of dark energy remains one of the major unanswered questions in physics. It may be a constant energy of empty space. It may involve a changing field. It may indicate that gravity behaves differently across the largest scales. Current observations are broadly consistent with a cosmological constant, but greater precision is needed to understand whether the behavior changes over time. The future of the universe depends partly upon this answer. If dark energy remains constant, expansion continues accelerating. Distant galaxy groups recede faster. More regions cross beyond the event horizon. The local group remains gravitationally bound. The wider universe gradually disappears from possible contact. If dark energy changes slowly, the future could be different. Expansion might accelerate more strongly, weaken, or behave in a way not yet anticipated. But no current evidence offers a practical route toward the observable edge. Even the more uncertain models preserve immense causal limitations. Under the simplest future, the sky changes gradually. The process is too slow to notice within one lifetime. Galaxies do not vanish suddenly. Instead, their light becomes increasingly redshifted. Expansion stretches the wavelength while it travels. Ultraviolet light becomes visible. Visible light becomes infrared. Infrared becomes microwave. Microwave becomes radio. Eventually, the wavelength becomes so long and the energy so low that detection becomes extraordinarily difficult. The light also arrives more slowly. Events within the distant galaxy appear increasingly stretched in time. 1 second there may correspond to a longer observed interval here. The galaxy seems to evolve more slowly as its signals weaken and redden. It does not freeze at one sharp boundary. It fades. Future observers receive older and more diluted information. Then the source slips below practical detection. A galaxy can remain physically present while becoming absent from every useful observation. In the far future, nearly all galaxies outside the local group will disappear in this way. The Milky Way and Andromeda will merge into one large galaxy. Smaller members of the local group will join or orbit the resulting system. To future astronomers living there, the observable night sky may contain no clear external galaxies. The cosmic web will no longer be visible. The evidence for universal expansion may become hidden. The cosmic microwave background will be stretched to wavelengths so enormous that ordinary detection becomes extremely challenging. Future scientists may look outward and conclude that their galaxy is the entire visible universe. They could develop gravity, stellar astronomy, and planetary science, but reconstructing the Big Bang and cosmic expansion might be far more difficult. Their observational window would be narrower than ours. This gives the current universe a temporary transparency. Humanity can observe galaxies across billions of light years, measure their redshifts, map clusters and voids, see earlier stages of galactic development, study the afterglow of the hot young universe. These clues allow the large-scale history to be reconstructed. The information will not remain equally accessible forever. Cosmic expansion is slowly carrying the evidence away. The journey toward the edge therefore faces two opposing processes. A spacecraft tries to move outward. The universe carries its destinations away. The craft could accelerate close to light speed, but its target belongs to a changing future. If the destination is outside the event horizon, no ordinary trajectory succeeds. If the target lies inside, the journey may still take an immense time. And during that journey, the boundary of future accessibility continues changing. Imagine a spacecraft launched toward a galaxy currently 14 billion light-years away. Under idealized conditions, that region may still be within the maximum causal reach of a signal sent now. But the route would demand motion extremely close to light speed for cosmic timescales. The craft must survive, maintain direction, avoid particles, continue through an expanding environment. A small delay in launch may matter cosmologically. A destination reachable now may become unreachable later as the universe evolves. A civilization cannot postpone every journey indefinitely. The accessible universe is not a fixed territory. It is a shrinking set of future connections. This does not mean the physical size around Earth shrinks. The observable universe continues gaining information from some regions. The proper distances to remote matter continue increasing. But the set of places that can be reached by signals launched today becomes limited. The distinction is between observation and influence. Earth may keep seeing new ancient light while losing the ability to affect its source. The universe becomes informationally rich and causally narrow at the same time. A telescope can receive a photon from a galaxy no spacecraft can ever visit. A historian of the cosmos can study a world forever separated from every future human action. This gives observation a special role. Seeing becomes the only form of connection. The galaxy's light is not merely an image. It is the final information that region may ever contribute to our history. Astronomers can measure its shape, star formation, chemical composition, black hole activity, gravitational lensing, perhaps atmospheric signatures of planets in exceptional cases. But no reply is guaranteed, no visit, no confirmation of what happens next. The observed galaxy becomes a preserved past without a shared future. An advanced civilization might respond to this by spreading early, long before accelerated expansion isolates distant regions. It could send probes toward neighboring galaxy groups while the routes remain open. Those probes may establish new outposts. Each outpost possesses its own future horizon. It can reach regions unavailable from the original home world. By expanding through a chain of locations, the civilization could influence a much larger volume than by waiting at one central planet. But even this strategy remains finite. The first probes must reach each region before causal separation becomes complete. The network grows below light speed. It cannot leap across already closed horizons. There is a maximum domain determined by the civilization's starting place and time. A civilization beginning billions of years earlier would have access to a larger region. One beginning far in the future would inherit a smaller cosmic island. Opportunity depends upon when intelligence appears. Humanity emerged during an era when many external galaxies remain reachable in principle, only a small fraction compared with the observable universe. Still, far more than will remain available in the distant future. The engineering required to reach them is beyond current ability. But cosmology does not forbid every outward path yet. A sufficiently patient civilization could spread through the local group, perhaps toward nearby external groups if missions began early and traveled rapidly enough. The practical territory remains enormous. The local group alone contains many galaxies, hundreds of billions of stars, possibly far more planets than humanity could explore in any familiar timescale. Cosmic limits do not create a small universe. They create a distinction between the enormous and the infinite. A civilization may never approach exhausting what remains available locally, yet the unreachable regions still matter philosophically. Their existence shows that reality can be larger than possible experience. There may be galaxies whose light never reaches Earth, worlds that remain outside every human observation, events that occur without entering our causal history. No technology built here can reveal them directly. Scientists may infer that such regions exist from the overall geometry, but their individual contents remain unknowable. The observable universe is not everything. It is everything that has been able to inform us. This idea applies to every observer. A civilization in a galaxy beyond our horizon possesses its own observable sphere. It may include regions hidden from Earth. From its perspective, Earth may lie beyond visibility. Each observer knows a different part of the total universe. No single telescope sees the whole. Even if civilizations exchanged data across all reachable space, their combined map would remain limited. Some regions could never join. Cosmic knowledge is permanently distributed. This also means there is no universal visible edge shared by every observer. Earth's observable boundary is centered on Earth. A traveler halfway across the universe carries a different horizon. New galaxies become visible ahead. Some galaxies behind may become unreachable. The spacecraft does not approach one common shell surrounding everything. Its window shifts. Suppose the traveler reaches a galaxy near the edge of Earth's observable region. From that new location, Earth would no longer appear central. The traveler could observe regions lying beyond Earth's original horizon. The journey would reveal more universe, but the new observer would still face a horizon roughly surrounding their own position. Beyond it, more unseen regions may exist. The traveler has not reached the end, only a new viewpoint. If the universe is infinite, this process never concludes. Every reachable location reveals another finite observable sphere within an endless whole. If the universe is finite but much larger than our horizon, many moves may reveal more without finding a boundary. If it is finite and unbounded, a traveler may never encounter an edge at all. Expansion complicates every possibility. The universe may grow while the traveler moves through it. A route that would circle a static finite universe may become impossible if expansion increases the total distance too rapidly. Even determining the global shape may be impossible from one observable region. The edge remains a question about geometry, rather than a destination. Could dark energy be used as propulsion? The idea is tempting. If dark energy drives accelerated expansion, perhaps a spacecraft could collect it, concentrate it, create expansion behind the ship and contraction ahead. A natural warp engine. But dark energy is not known to behave like ordinary fuel. It does not appear as a wind flowing through space. No known device can scoop it into a tank. Its density, if described by the cosmological constant, is extraordinarily small on laboratory scales. Its influence becomes important only because it fills enormous volumes. Across a room, gravity and electromagnetic forces overwhelm it completely. Across billions of light-years of near-empty space, it shapes the cosmic future. A spacecraft cannot simply open a sail and ride dark energy outward. It is already part of the expanding universe. Every distant destination is affected too. Using expansion for travel would require controlling space-time locally, with precision and intensity far beyond anything demonstrated. The natural acceleration of the universe carries distant galaxies away from us. It does not carry a traveler conveniently toward them. A boat benefits from a river when the river flows toward the destination. Cosmic expansion increases the separation between traveler and distant target. It is more obstacle than current. There is no universal outward direction from a center. Every unbound region recedes from every other. A traveler leaving Earth cannot choose to move with expansion toward the edge because no singular outer edge exists. Expansion occurs throughout the space between large structures. The farther the traveler moves, the more space may remain ahead. This is why the universe can expand without developing an empty region behind the galaxies. The galaxies are not moving into a previously vacant exterior. The distances within the universe increase. If space is infinite, it may always have been infinite while becoming less dense. An infinite line can expand by increasing every separation between marked points. It remains infinite before and after. No outer boundary moves. If the universe is finite, its volume can increase without requiring an edge within the geometry. Both possibilities resist ordinary pictures. Human imagination wants to view the universe from outside, see it growing like a sphere. But cosmology provides no confirmed external viewpoint. The expansion is measured from within. Redshifts, distances, the cosmic microwave background, the distribution of matter. These internal observations reveal changing scale. No outer camera is required. For the traveler, only local space is directly experienced. Inside the spacecraft, objects remain stable. A ruler does not expand. The engine does not stretch automatically. The travelers do not feel a cosmic force pulling their bodies apart. Expansion appears through the changing relationship with remote unbound galaxies. The stars within the current galaxy remain together. The wider clusters move. This makes the cosmic horizon almost invisible physically. No alarm sounds when one galaxy crosses it. No flash marks the final possible message. The transition is defined mathematically. At one stage, a light signal sent now can eventually arrive. Later, the same journey becomes impossible. Nothing local happens at the source or receiver. The future geometry between them changes. A door closes without a wall moving across the sky. The galaxies may remain visible for billions of years after this causal separation. Observers have no immediate sign that communication has become impossible. Only cosmological measurement reveals it. This quietness makes the expanding universe feel both calm and immense. Nothing rushes in the local sky. The great separation happens over billions of years. Galaxies drift through mathematical distance. Their light reddens, horizons form, future paths disappear. No sound, no sudden darkness, only the gradual unfolding of space-time. Imagine one distant galaxy visible through a powerful telescope. Its light began traveling when the universe was young. The image contains bright regions of star formation, gas clouds, perhaps early planets. The photons enter the detector tonight. They end a journey lasting most of cosmic history. The galaxy that released them is now much farther away. Its present stars may be entirely different. Any civilization that existed there then may be gone. Any civilization living there now is beyond our reach. Earth receives the ancient image, a final connection between two regions that no longer share a possible future exchange. The telescope cannot change that galaxy, but it can preserve what arrived. Measure it, learn from it. The observation becomes part of humanity's knowledge. Perhaps reaching the edge was never the only form of exploration. A photon can bring the distant universe to us, not physically, informationally. Telescopes collect journeys that spacecraft could never complete. Each photon is a messenger that crossed expansion successfully. It carries the temperature of a star, the chemistry of a galaxy, the shape of a gravitational field, the history of the early cosmos. Humanity may never stand within those regions, but we can still understand part of them. The expanding universe limits travel more strongly than observation, and observation turns unreachable places into knowable ones, at least partially. This may be the most realistic way humanity approaches the cosmic horizon, not by racing toward it, by allowing its ancient light to arrive, building better receivers, detecting longer wavelengths, combining telescopes across Earth and space, reading the information carried by photons, particles, and gravitational waves. The edge comes toward us through evidence. We do not reach the ancient universe. The ancient universe reaches our instruments. The next part of this journey will follow those distant signals backward toward the earliest observable era, exploring the cosmic microwave background, the universe before stars, and why looking farther does not reveal a wall but an increasingly young and opaque cosmos. Looking farther into space does not eventually reveal a wall. It reveals a younger universe. Nearby galaxies appear relatively recent. More distant galaxies appear as they were billions of years ago. Farther still, the first generations of stars begin to disappear. The cosmos becomes darker, simpler, hotter, and eventually ordinary visible light can no longer carry the journey backward. At that point, telescopes encounter the cosmic microwave background, a faint glow surrounding Earth in every direction. It does not come from one star, one galaxy, or one distant location. It comes from nearly the entire early universe. The light was released when the cosmos was about 380,000 years old. Today, the universe is roughly 13.8 billion years old. The difference is enormous. The cosmic microwave background allows astronomers to observe a universe far younger than the first planets, galaxies, or stars. It is a picture of the cosmos before the familiar night sky existed. At that time, matter was spread more evenly. Small variations in density were present. Some regions contained slightly more matter, others slightly less. Over billions of years, gravity amplified these tiny differences. Denser regions attracted additional matter. Gas gathered. Stars formed, galaxies emerged, clusters and vast cosmic filaments slowly developed. The complicated structure visible today began as subtle patterns within this ancient radiation. The cosmic microwave background is therefore both an image and a record. It shows the early universe. It also contains the seeds of the later one. But it is not the edge. It is not the first instant of existence, and it is not a surface located at one permanent distance. The light surrounds every observer, because every observer looks backward into the same early cosmic era. A civilization in another galaxy would also see a cosmic microwave background around itself. Its ancient light would come from a different spherical region centered upon that observer. The surface belongs to the observer's past light cone. It is a boundary in time and visibility, not a shell physically surrounding one special point. To understand why this ancient light forms a limit, imagine the early universe before it became transparent. Matter existed as a hot plasma. Atomic nuclei moved among free electrons. Photons traveled only short distances before scattering from charged particles. Light could not move freely through space. It bounced repeatedly. Direction was lost. The universe behaved somewhat like the interior of a dense glowing fog. The fog itself emitted light, but no clear distant image could pass through it. As the universe expanded, it cooled. Eventually, electrons combined with atomic nuclei. Neutral atoms formed, with fewer free electrons available to scatter photons. Light could begin traveling across great distances. The universe became transparent. The photons released during this transition continued moving. Cosmic expansion stretched their wavelengths. What began largely as much hotter radiation gradually shifted into microwave frequencies. Those photons now reach radio and microwave telescopes. Their present temperature is only about 2.7 degrees above absolute zero, a cold afterglow of a once hot cosmos. The microwave background appears extremely uniform. Its temperature is nearly the same in every direction, but not exactly. Tiny differences are present, only a few parts in 100,000. These small variations reveal where matter was slightly denser or thinner. Without them, gravity would have little structure to amplify. The universe might have remained almost perfectly smooth. No galaxies, no stars, no planets. The small irregularities became the foundation of everything later. Every galaxy in the observable universe is connected, historically, with those early variations. The Milky Way, Andromeda, the most distant galaxies visible to modern telescopes, all developed from matter shaped by the young cosmos. This makes the microwave background one of the most important observations in science. It provides evidence for an early hot universe. It allows measurements of cosmic geometry, matter content, expansion history, and the statistical structure from which galaxies formed. Yet the image has a strange quality. The material producing the background is now much farther away than it was when the photons began their journey. At emission, those regions were separated from the matter that later became Earth by tens of millions of light-years in the relevant cosmological distance measure. Today, because space expanded, the matter associated with the observed background lies tens of billions of light-years away. The light did not cross a static distance. The entire scale changed while it traveled. Again, the cosmic edge becomes a history of expansion rather than a simple number. A traveler cannot fly to the microwave background as it appears in the sky. That glowing surface is an image of a time. If a spacecraft moves toward the region from which one part of the background arrived, the craft does not approach the young universe. The young universe is already gone. The spacecraft moves toward the modern descendants of that region. Galaxies, clusters, expanding space, perhaps matter now beyond reach. The background is not waiting ahead. It is arriving from behind in time. This is one of the clearest examples of why seeing and visiting are different. A telescope receives the past. A spacecraft can only enter the future. No engine can travel to an earlier cosmic era simply by moving farther away. The oldest visible light is old because of travel time, not because the early universe exists as a distant place still preserved in its original form. Every region of the universe was once hot and dense. The Milky Way's matter was also part of that young plasma. The early universe did not happen at one distant point. It happened everywhere. The microwave background seems remote because observers see distant matter as it was then. Local matter evolved around us and no longer appears in that early state. This removes another misleading picture. The Big Bang was not an explosion at one location sending galaxies into surrounding emptiness. The early hot state filled space. Expansion occurred throughout the universe. Every large region has been moving away from many others as the scale grew. Looking outward reveals earlier history because distant light needed longer to arrive. It does not point toward one birthplace. There is no known central scar in the sky, no direction leading back to the origin. Every direction leads backward in time. The farther telescopes look, the more similar the broad cosmic age becomes. Eventually, all directions reach the era of the microwave background. Beyond that surface, ordinary light cannot provide direct images. But this does not necessarily mean all information is inaccessible. Other cosmic messengers may have traveled through the early plasma more freely. Neutrinos interact only weakly with matter. A background of ancient neutrinos is expected to exist from a time when the universe was only seconds old. Detecting it directly would be extraordinarily difficult. The particles are faint, cold, and difficult to distinguish from other sources. Yet they may carry information from an era much earlier than the microwave background. Gravitational waves may reach even deeper. Ripples in spacetime can travel through matter with little disturbance. If powerful gravitational processes occurred during the earliest moments, some of their waves may still cross the universe today. Future observatories may detect a background of these ancient distortions. Such a discovery would not create a photograph in the ordinary sense. It would reveal patterns, energy scales, symmetry, perhaps evidence of inflation or other early universe processes. The cosmic horizon of observation can therefore depend upon the messenger. Visible light encounters one limit. Microwaves reveal the transparency transition. Neutrinos may reveal an earlier stage. Gravitational waves may reveal earlier conditions still. Every new messenger opens a different window, but even these windows have boundaries. The very earliest moments may remain hidden behind limits in theory and observation. At sufficiently high energies, general relativity and quantum mechanics must both become important. These two great frameworks describe nature extremely well in their tested domains, yet they do not form a complete unified description of the earliest possible universe. Gravity shapes spacetime. Quantum theory shapes particles and fields. Near the first fractions of a second, both may have operated in ways not yet fully understood. A complete theory of quantum gravity may be required. Without it, asking what happened at the absolute beginning may exceed present physics. The equations of classical general relativity, when traced backward, lead toward a state of extreme density, often described as a singularity. But a singularity may signal that the theory has been extended beyond where it can be trusted. It may not represent a literal physical point of infinite density. Quantum effects could replace it with another structure, a bounce, a transition, an earlier phase, or something for which present language has no accurate picture. No confirmed observation yet decides among these possibilities. The observational edge is therefore accompanied by a theoretical edge. The oldest information grows harder to obtain, the physical conditions become more extreme, the mathematics becomes less complete. Looking farther does not reveal a final wall. It reveals a region where familiar descriptions gradually lose power. This limit is different from the event horizon created by accelerated expansion. The cosmological event horizon separates future influence. The early universe opacity separates present electromagnetic observation from earlier history. The particle horizon limits how far information has traveled since the beginning of the observable era. Several boundaries overlap within cosmology. Each answers a different question. How far can light have reached us? How far can signals sent now travel? How far back can ordinary photons reveal? Which regions have ever been causally connected? Calling all of them the edge hides these differences. The universe has no single edge in the simple sense. It has horizons, surfaces of last interaction, limits of future communication, and boundaries of current theory. A spacecraft cannot reach the microwave background. A telescope cannot receive a present-day message from beyond the event horizon. A physicist cannot yet describe the earliest moment with confidence. Each limit arises differently. This makes cosmic exploration a combination of travel, observation, and inference. Travel carries instruments to new locations. Observation receives ancient messengers. Inference connects what can be measured with what cannot be seen directly. Most knowledge of the early universe comes from traces left in later conditions. The distribution of galaxies, the abundance of light elements, the microwave background, the expansion rate. These are like clues preserved after an event. The first moments are not watched directly. Their consequences remain. This is how science often reaches inaccessible places, not by standing there, by studying what arrived. A black hole's interior cannot be viewed directly from outside. Its mass and spin affect surrounding matter. The core of the sun cannot be photographed through ordinary light. Neutrinos and surface vibrations reveal its conditions. The early universe cannot be visited. Its relics remain within the sky. The farther back the evidence leads, the more carefully different observations must agree. One measurement alone can be ambiguous. Several independent clues can support one history. The expansion of galaxies, the cosmic microwave background, the proportions of hydrogen, helium, and other light nuclei, the growth of large-scale structure. Together they form a consistent picture of an expanding universe that began in a much hotter and denser state. The story is powerful not because one telescope saw the beginning, because many present observations point toward the same past. Could a civilization travel beyond the microwave background surface and see something older? From its new location, it would possess a new observable sphere. It might receive ancient light from regions hidden from Earth, but it would still see its own surface of last scattering. The early opaque era surrounds every observer's view into the past. Moving through space changes which regions are sampled. It does not remove the historical opacity. The traveler cannot step outside cosmic time. Every location has its own past. The same early transition limits ordinary light everywhere. This means no collection of spacecraft can photograph the universe before it became transparent, using photons that did not travel freely then. A broader network could sample more regions of the last scattering surface. It could compare different viewpoints, yet the earlier plasma would remain hidden to electromagnetic sight. Technology may widen access. Physics still defines the channel. The observable universe is therefore not only limited by distance, it is limited by what information can survive. Photons scatter, signals redshift, structures evolve, horizons separate. Some events leave clear relics, others may leave none detectable. The universe may contain parts of its own history that no future observer can reconstruct fully. This is not because knowledge is unimportant, it is because information can be physically lost from accessible regions. Light can cross a horizon, matter can collapse into a black hole, quantum details can become scrambled. Cosmic expansion can carry signals beyond recovery. Reality can contain more history than any one observer can know. Even so, the microwave background offers an extraordinary reach. A faint signal, only a few degrees above absolute zero, carries information from a time before stars. Every direction in the sky contains it. Behind the visible galaxies, behind the Milky Way, behind daylight. The ancient glow passes through the solar system continuously. Specialized instruments separate it from nearby radio emission and foreground dust. The early universe is not visually distant in one direction. Its afterglow surrounds the planet. Earth moves through this radiation. The solar system's motion causes one side of the background to appear slightly warmer, and the opposite side slightly cooler. After this motion is removed, the remaining pattern reveals the early cosmos. A civilization can measure its own movement relative to the large-scale cosmic background. Not an absolute state of rest forbidden by relativity, but a convenient cosmological frame in which the ancient radiation appears most uniform. The background becomes a reference for the universe's large-scale structure, a kind of ancient map beneath all later motion. Perhaps future travelers would use it for navigation. The pattern would change slowly as they moved to new regions. Different sections of the early universe would enter view. The microwave background could help identify location across cosmological distances, but it would not point toward an edge. Every destination would still be surrounded by an ancient glow. Every observer would remain centered within their own visible past. This repeated centeredness can feel confusing. Earth appears central. A distant galaxy appears central to its own observers. A spacecraft appears central after moving between them. There is no contradiction. The observable sphere is defined by arriving information. Every observer occupies the endpoint of their own received light. The center belongs to observation, not necessarily to the entire universe. A physical cosmic center may not exist. If the universe is spatially infinite and broadly homogeneous, no location is preferred. If it is finite and unbounded, every location may still be equivalent on large scales. The background's uniformity supports the idea that the universe is similar in broad statistical form across great distances. But one mystery follows. Why are regions of the early universe so similar if some were apparently too far apart to exchange light before the microwave background was released? This is known as the horizon problem. Opposite directions in the sky have nearly the same temperature. Yet under a simple expansion history, those regions may not have been in causal contact early enough to reach equilibrium. How did they become so uniform? Cosmic inflation offers one possible answer. Inflation proposes that the very early universe underwent a brief period of extremely rapid expansion. Before this expansion, regions now separated across the sky could have been close enough to interact. They reached similar conditions. Then inflation stretched them far apart. Tiny quantum variations were also stretched to cosmic scales. These variations may have become the seeds later seen in the microwave background. Inflation can explain several observed features elegantly. The large-scale flatness of space, the broad uniformity of the cosmic background, the origin of primordial density fluctuations. Yet the exact mechanism remains uncertain. The field responsible has not been identified conclusively. Different inflationary models make different predictions. Scientists search the microwave background and large-scale structure for evidence capable of distinguishing them. Inflation also changes how the observable universe is imagined. The region visible today may have begun as a tiny portion of a much larger expanding cosmos. The full universe could extend far beyond our horizon, perhaps vastly farther. In some models, inflation continues in other regions, creating an enormous collection of cosmic domains. But these possibilities remain beyond direct confirmation in their broadest forms. The observable universe provides only one accessible patch. Its uniformity and small irregularities carry clues. The whole remains hidden. The journey to the edge therefore becomes more distant conceptually. Even reaching the limit of visible matter would not reveal the total universe. The observable sphere may be one small region within a far larger structure created during inflation. There could be no nearby outer boundary, only more space extending beyond every horizon. A traveler cannot use the microwave background as a doorway into those regions. The background is evidence of their shared early history, not a passage. The next part of this journey will examine the possible size and shape of the entire universe, asking whether space may be infinite, curved, or finite, without boundaries, and why even a complete journey in one direction might never encounter an edge at all. The universe may be much larger than the region humanity can observe. It may even be infinite, but infinity is not the only possibility. Space could be finite while having no boundary. A traveler might continue moving without ever encountering a wall. This sounds contradictory, because ordinary finite objects have edges. A table has sides, a room has walls, a planet has a surface separating it from the surrounding space. But the geometry of the universe does not need to resemble an ordinary object inside a larger container. Its distances and directions can be defined from within. To imagine this, begin with the surface of Earth. Earth's surface has a finite area. A traveler can measure it, map it, cross it. Yet there is no edge on the surface where the ground suddenly ends. A person walking continually east does not arrive at a border of the planet's two-dimensional surface. Eventually, the traveler circles the globe and returns to the starting region. The surface is finite but unbounded. It has limited size, no boundary. The full universe could possess a three-dimensional version of this property. A spacecraft might move in one direction through space, and after an immense journey, return from the opposite direction. No turn would be required. No wall would be crossed. The route would close because of the global shape of space. This analogy must be handled carefully. Earth's surface curves through the larger three-dimensional space familiar to us. But a three-dimensional universe does not necessarily need to curve into a fourth ordinary spatial dimension that could be physically entered. Its curvature can be described internally. Observers can measure angles, distances, the paths of light, the behavior of parallel lines. These measurements reveal geometry without requiring an external viewpoint. A creature living only on Earth's surface could discover that the surface is curved. It could draw a large triangle, measure the angles. On a flat sheet, the angles add to 180 degrees. On a sphere, a sufficiently large triangle has a greater total. The creature can infer curvature while remaining on the surface. Astronomers attempt something similar with the universe. They examine how light travels across cosmic distances. They compare the apparent size of known patterns with theoretical expectations. They study the cosmic microwave background, the distribution of galaxies, gravitational lensing, and the history of expansion. These measurements indicate that the observable universe is very close to spatially flat. On large scales, triangles behave approximately as they do in ordinary Euclidean geometry. Parallel light paths do not appear to converge or diverge strongly because of global curvature. But nearly flat does not necessarily mean infinite. A very large curved surface can appear flat across a small region. Standing in an open field, Earth's surface seems level. Its curvature becomes evident only across much greater distances. The observable universe may be a relatively small portion of a much larger curved whole. If the total curvature radius is far larger than the observable region, present measurements would detect little deviation from flatness. A finite universe could therefore appear almost perfectly flat. Another possibility is a universe that is exactly flat but still finite because of its topology. Geometry describes local properties. Topology describes how space is connected globally. A flat sheet appears infinite if it extends endlessly. But imagine identifying opposite edges. A traveler leaving through the right side re-enters from the left. Leaving through the top returns from the bottom. The surface can be finite while remaining locally flat. A familiar shape related to this idea is a torus, the surface of a donut. A torus is finite and unbounded. Its geometry is not perfectly flat when embedded in ordinary space, but an idealized flat torus can be described mathematically by joining opposite edges of a flat rectangle. A three-dimensional version could connect opposite faces of a cosmic volume. A spacecraft leaving one side would eventually return through the other. Locally, space could look ordinary. Globally, it would wrap around. If the universe had this kind of structure and were not too large, astronomers might observe repeated images of the same galaxy. Light could reach Earth along more than one route. One path may cross space directly, another may circle the universe before arriving. The same object could appear in different directions. Each image might show the galaxy at a different age, because the paths have different lengths. A single galaxy could look like several unrelated objects. One image might show it before a major merger, another after. A repeated pattern could appear within the cosmic microwave background. Astronomers search for such signatures. So far, no confirmed repeating pattern has revealed a small wrapped universe. This suggests that if space has a repeating topology, Its characteristic scale may be larger than the observable region, or its structure may be arranged in a way that makes the pattern difficult to detect, or space may simply not wrap around in this manner. The lack of a detected pattern does not prove infinity. It places limits on certain finite models. The total universe may extend far beyond the distance from which light has reached us. If it is large enough, no repeated image has had time to arrive. The observable sphere would remain too small to reveal the global connection. This returns us to the difference between the universe and the observable universe. The observable universe is limited by the travel time of information. The entire universe is the full spatial and temporal structure, whether visible or not. Human measurements apply directly only to the observable region. Cosmologists often assume that the wider universe resembles the part we can see on sufficiently large scales. Matter is distributed statistically in similar ways. The same laws of physics operate. No location is fundamentally preferred. This assumption is supported by the broad uniformity of observations. The cosmic microwave background looks nearly the same in every direction. Galaxies form similar large-scale patterns across the sky. But any conclusion about regions beyond observation includes an element of extrapolation. They cannot be inspected directly. Perhaps the universe continues in broadly the same way. Perhaps conditions eventually differ. Science favors the simplest model consistent with evidence. It remains open to new observations. If space is infinite, it may contain infinitely many galaxies, infinitely many stars, and perhaps infinitely many regions resembling the observable universe. The idea becomes difficult to picture because infinity is not merely an extremely large number. It has no final amount, no farthest galaxy, no last cluster. A traveler can continue forever. Every distance crossed leaves more distance ahead. Even a spacecraft moving forever would never complete the journey across an infinite universe. There is no total crossing, no opposite edge, no moment when everything lies behind. The phrase reaching the edge would have no physical destination. It would resemble counting toward the final whole number. No matter how high the count rises, another number remains. An infinite universe may also lead to unusual questions about repetition. If the laws of physics allow only a finite number of possible arrangements within a finite region, then sufficiently distant regions might repeat arrangements. A world resembling Earth, a galaxy resembling the Milky Way, perhaps histories that appear similar for long periods. But these arguments depend upon assumptions about quantum states, probabilities, and the nature of infinite space. They do not mean an exact duplicate of Earth has been observed. Any such region would likely lie unimaginably far beyond the observable horizon. No signal could connect the two. The idea belongs to theoretical reasoning rather than practical exploration. Even in an infinite universe, our causal region remains finite. Infinity beyond the horizon does not increase what Earth can reach. A small illuminated circle can exist inside an endless landscape. The landscape has no outer border. The visible area remains limited. Cosmic expansion may isolate every observer within a bounded future, even if space itself extends without end. Infinity and accessibility are therefore separate. The universe can be infinite while the reachable universe is finite. It can contain endless matter while every civilization possesses only a limited causal neighborhood. An infinite universe does not guarantee endless travel opportunities from one starting point. Dark energy may prevent access to almost all of it. A spacecraft can travel outward for an immense time, but it remains within the portion connected to its original path through spacetime. Regions beyond the event horizon separate too rapidly. Their existence adds to the universe, not to the traveler's possible destinations. If space is finite and positively curved, the geometry may resemble a three-dimensional analog of a sphere. There would be a total volume, no boundary. On sufficiently large scales, initially parallel paths could eventually converge. Large triangles could have angles totaling more than 180 degrees. Light might circle the universe under appropriate conditions. A traveler moving in a straight line could, in principle, return to the starting point, but expansion complicates the journey. The universe may grow faster than the traveler can complete the circuit. Even light may fail to travel all the way around before cosmic acceleration stretches the route beyond reach. A closed spatial shape does not guarantee practical circumnavigation. Earth's surface can be crossed because its size remains nearly stable while the traveler moves. A cosmic space may expand dramatically during the journey. The destination, which is also the starting point approached from the other side, continually moves farther away in the evolving geometry. A finite universe could therefore be unbounded and still impossible to circle. The global path exists mathematically. The physical traveler cannot complete it. If space has negative curvature, it would behave differently. Parallel paths tend to diverge. Large triangles have angles totaling less than 180 degrees. The geometry is sometimes compared with a saddle-shaped surface. But a two-dimensional saddle is only an analogy. Three-dimensional negatively curved space is more difficult to visualize. Such a universe may be infinite. It may also possess certain finite topologies. Again, curvature alone does not determine total size. Different global structures can share the same local geometry. Observations currently place strong limits on large curvature. The visible universe appears close to flat. This means any positive or negative curvature is subtle across the region we can measure. The distinction may become detectable with more precise observations, or it may remain forever beyond reach if the curvature scale greatly exceeds the horizon. There is a fundamental limitation here. To determine the shape of an object fully, an observer often needs access to a large fraction of it. Humanity sees only one cosmic region. The horizon may be far smaller than the total structure. Trying to determine the whole universe from one observable patch can resemble trying to learn the shape of Earth from one small field. Careful measurements might reveal slight curvature, but if the planet were vastly larger, the field could remain nearly flat within every available instrument. The observer might never know whether the surface closes far away. Cosmologists therefore describe possible models rather than claiming direct knowledge of the entire shape. The data support some possibilities more strongly, rule out others, and leave several open. This uncertainty is not a weakness. It reflects the honest boundary between evidence and extrapolation. The observable universe is already vast enough that even detecting global curvature requires extraordinary precision. The microwave background provides one of the best tools because it contains a known statistical pattern. The apparent angular size of features within that pattern depends upon the geometry through which their light traveled. In positively curved space, light paths converge, making features appear larger. In negatively curved space, they diverge, making features appear smaller. In flat space, the pattern appears at the expected scale. Measurements align closely with flat geometry. But the remaining uncertainty permits a universe much larger than the visible sphere, perhaps hundreds of times larger in volume, perhaps vastly more, perhaps infinite. There may be regions so far away that the light traveling toward Earth will never arrive, not merely because it has not arrived yet, because accelerated expansion prevents it. Those regions never enter our observable history. Their galaxies may emit light in our direction for billions of years. The distance between us grows too rapidly. The photons make local progress. The expanding geometry carries the destination away. The signals remain forever outside. No future telescope on Earth can detect them. A traveler beginning here cannot visit them. The wider shape may include them. Our experience never will. This creates an important distinction between what exists and what can be empirically confirmed. Science studies reality through observations and testable consequences. A region permanently disconnected from us cannot be observed directly. Its specific properties cannot be measured. Scientists may infer its likely existence from theories describing the accessible region, but the inference remains different from detection. A model may predict endless space. Another may predict an enormous finite space. If both produce identical observations within our horizon, no present experiment distinguishes them. The question may remain open. Some questions in cosmology may not be answered by building a larger telescope alone. A larger telescope collects fainter light. It cannot receive light that never arrives. A detector can become more sensitive. It cannot cross a causal boundary. The universe may contain truths that leave no observable trace within our region. This does not stop scientific progress. It clarifies which questions are accessible. The age of stars can be measured. The expansion history can be constrained. Dark matter can be mapped through gravity. The cosmic microwave background can reveal early conditions. but the exact total volume of all space may remain unknown. The absence of a known boundary also affects the question of what lies outside the universe. If space is infinite, there is no outer region. The universe continues. If space is finite but unbounded, there is still no edge requiring an exterior. Earth's two-dimensional surface does not need another point on the surface beyond its northernmost latitude. The path simply changes direction within the geometry. Similarly, three-dimensional cosmic space may close upon itself without opening into an external emptiness. An outside may exist within a higher dimensional theory, but it is not required for the universe's internal geometry. The word universe can also be used in different ways. Sometimes it means all physical reality. In that definition, asking what lies outside it becomes self-contradictory. Anything physically real would already belong to the totality. In other contexts, the observable universe means our visible region. Something can clearly lie beyond that. More galaxies, more space, perhaps other domains. Confusion often arises when these meanings are combined. The edge of the observable universe is not the edge of all existence. The boundary of our information is not necessarily a boundary of reality. Some theories propose additional cosmic regions produced by inflation. Inflation may end in one region while continuing elsewhere. New expanding domains form. Each may develop different local conditions. These ideas are sometimes grouped under the term multiverse, but the word covers many different proposals. Some involve regions of one larger inflating spacetime. Others involve quantum interpretations. Others arise from higher dimensional models. They should not be treated as one confirmed object. No direct observation has established a neighboring universe. The hypotheses emerge from attempts to understand existing theories. They may have indirect consequences, or remain beyond testing. If an inflating cosmos contains many domains, our observable universe may be one small area within a much larger structure. The apparent edge is then even less like a boundary. Beyond it may lie more of our own domain. Farther still, perhaps regions with different histories. But no spacecraft can simply fly through the observable horizon to inspect them. Inflationary separation and accelerated expansion may place them permanently outside causal contact. The theory expands the conceptual universe, not the accessible route. Higher dimensional models create another possibility. Our familiar three-dimensional space may be part of a larger geometry. Additional dimensions could be compact and tiny. Or our universe may resemble a lower dimensional region within a higher dimensional space. In some models, gravity can interact with these dimensions differently from ordinary matter. Such ideas attempt to address questions about particle physics, gravity, and the early universe. They are mathematically rich. None currently provides a verified road beyond the cosmic horizon. An additional dimension would not automatically function like a hidden corridor. The traveler would require a physical mechanism to enter it, navigate it, and return. The required conditions may not exist for ordinary matter. Once again, a possible mathematical structure is not yet a transportation technology. The search for the universe's shape therefore remains observational rather than exploratory in the spacecraft sense. Astronomers look for repeated patterns, measure curvature, study the largest structures, test whether physical laws appear consistent across direction and distance. The results so far suggest a universe that is broadly homogeneous and very close to flat across observable scales. No clear sign of a nearby global boundary appears. No repeated cosmic image has confirmed a small wrapped space. The simplest picture is that the universe extends far beyond what can be seen, perhaps without end. For a traveler, this means there may be no final destination called the edge. Suppose a spacecraft could ignore fuel limits and continue indefinitely. It leaves the Milky Way, crosses the local group, moves through the space between galaxy clusters. Behind it, the home region fades. Ahead, new structures appear, if they remain causally accessible. The traveler expects eventually to find the last galaxy, but after every cluster lies another region, or expansion creates a horizon before the next region can be reached. The journey ends not at a wall. It ends when no additional destination remains connected to the spacecraft's future. The limit is causal rather than spatial. The ship may continue moving through emptier local space, but the broader universe recedes beyond contact. The traveler does not reach the end of existence. only the end of available connection. If space wraps around, a different outcome is possible. The traveler follows what appears to be a straight route. After immense time, familiar structures may appear ahead, not because the ship turned around, because space reconnects. The home galaxy could be seen from the opposite direction, but recognizing it would be difficult. Billions of years may have passed. The galaxy may have merged. Its stars may have changed. The spacecraft may return to a descendant of home that looks entirely unfamiliar. A closed route through space is still an open journey through time. The traveler cannot return to the original moment. Circumnavigation does not restore the past. This reinforces the quiet relationship between cosmic distance and cosmic history. Every attempt to map the universe involves time. The farther the view, the older the image. The longer the journey, the later the arrival. A global shape cannot be explored as though frozen. Space evolves while it is measured. The map changes during the expedition. A line drawn across the cosmos is a path through space-time, not merely through space. Perhaps this is why the edge remains elusive. We imagine a snapshot, a complete universe existing at one shared moment, a traveler moving across it like a person crossing a room. Relativity does not provide one universal division into space and time for every observer. Cosmic expansion offers a useful large-scale time coordinate, but any real journey unfolds within the changing geometry. The destination's position, age, and accessibility depend upon the route. The universe is not a fixed object waiting to be crossed. It is an evolving space-time. Its shape includes history. A final map would need to show not only where every galaxy is, it would need to show every event, every possible path of light, every horizon, every region that can influence another. The full structure is four-dimensional. A spacecraft follows one thread through it. From within that thread, only part of the whole becomes visible. The traveler can change position, not step outside space-time to view the complete design. No observer receives a privileged external perspective. Every map is constructed from inside the universe. Every measurement arrives through signals. Every conclusion respects the time those signals required. This may feel limiting, but it also gives cosmology its unusual beauty. The universe reveals its shape indirectly, through ancient light, through tiny temperature variations, through the paths of galaxies, through the way gravity bends distant images, through the silence beyond a horizon. The edge is studied through what cannot happen as much as through what can. A message fails to arrive. A repeated pattern does not appear. A triangle retains nearly Euclidean angles. A galaxy's light becomes redshifted. Each clue narrows the possibilities. For now, the global universe remains open. It may be infinite. It may be finite and unbounded. It may possess a subtle topology larger than the observable region. What can be said with confidence is that no nearby physical edge has been detected. The visible horizon is not a wall, and traveling toward it would not reveal an exterior. The spacecraft would enter new regions, carry a new horizon, and continue within the same evolving cosmos. The next part of this journey will explore what the traveler might actually experience after billions of years. The changing life of stars, the merging of galaxies, the fading of the cosmic background, and the distant future of a universe that continues expanding long after the original destination has vanished from view. A traveler moving toward the farthest reachable regions would not enter a universe preserved in the conditions seen from Earth. The journey itself would consume cosmic time. While the spacecraft moves, stars continue aging, galaxies continue merging, black holes continue growing, and the expansion of space continues carrying distant structures away. The destination changes before the traveler arrives. This is true even for nearby stars. A telescope sees a star as it was years ago. A spacecraft reaches it years later. Across one galaxy, the delay may become tens of thousands of years. Across intergalactic space, it may become millions or billions. The farther the journey extends, the less the original image resembles the place waiting at the end. A distant galaxy observed today may appear bright with young blue stars. Its shape may be irregular. Gas clouds may be colliding. A central black hole may be feeding intensely. But the light showing these features began its journey long ago. By the time a spacecraft could arrive, the bright stars may have died. The gas may have settled. The galaxy may have merged with another. Its central black hole may have entered a quiet stage. The traveler is not moving toward a photograph. The traveler is moving toward the future descendant of the photograph. This difference becomes especially important when the journey lasts billions of years. The universe evolves on that scale. Stars do not shine forever. Galaxies do not keep the same form. The night sky itself changes. A star remains luminous only while it has fuel available for nuclear fusion. The most massive stars burn quickly. They may live for only a few million years. Their bright light is temporary. Smaller stars use fuel more slowly. A star like the Sun remains stable for billions of years. Red dwarfs, which are smaller and cooler, may continue shining for trillions of years. They consume their hydrogen gradually and efficiently. The future universe may therefore remain illuminated long after stars like the Sun have disappeared. But the character of that light will change. The brightest short-lived stars will become rare. Large clouds of fresh gas will gradually be used. Star formation will slow. Galaxies will contain older and dimmer populations. A traveler arriving in the distant future may find a quieter cosmos than the one visible from Earth today. The Milky Way itself will not remain unchanged. Andromeda is moving toward it. Over the next several billion years, the two galaxies are expected to pass through one another and eventually merge. Individual stars are separated by such enormous distances that direct stellar collisions will remain unlikely. But the large gravitational structures will interact strongly. The shapes of both galaxies will be transformed. Long streams of stars may extend outward. Gas clouds may compress and form new stars. The central black holes may eventually approach one another. After repeated passages, the galaxies will settle into one larger system. The familiar spiral shape of the Milky Way will no longer exist. The night sky from a surviving planet could become filled with the glowing band of another galaxy passing across it. Later, the stars of both systems would mix. A future civilization might not speak of the Milky Way and Andromeda as separate homes. It would inhabit one merged galactic structure. The local group may continue evolving in this way. Smaller galaxies orbiting nearby may be absorbed. Their stars will become part of the combined system. Gravity will preserve this local island, even as distant groups recede. The merged galaxy will remain bound. Its stars will orbit within one shared gravitational field. Outside it, the expanding universe will become increasingly empty from the local point of view. A traveler remaining within the local group will still possess enormous territory. Many stars, planetary systems, stellar remnants, black holes, perhaps civilizations, but the wider cosmic landscape will slowly fade. The local group will become more isolated. The great cosmic web visible to present telescopes will stretch beyond practical observation. The traveler may look outward and see fewer external galaxies, then almost none. This does not happen because the galaxies stop existing. Their light becomes too redshifted and faint. The distance grows. The rate of arriving information decreases. Eventually, their signals fall below every realistic detector. The wider universe becomes hidden behind expansion. A spacecraft launched during that future era would begin with less knowledge than humanity possesses today. Its astronomers might not know that billions of galaxies once filled the visible sky. They might observe only their own merged galaxy. The universe could appear like an immense dark emptiness, containing one island of stars. Evidence of the Big Bang would also become harder to detect. The cosmic microwave background continues cooling as the universe expands. Its wavelengths stretch. Its photons lose energy. In the far future, the signal may become so faint and long-waved that it blends with other limits of detection. Future scientists may struggle to recover the early history. The expanding universe gradually erases its most obvious records. A traveler leaving today carries something valuable, a map of a cosmic era that will not remain visible forever. Observations of distant galaxies, measurements of expansion, images of the microwave background, the chemical history of stars. These records could preserve knowledge after the original evidence fades. A sufficiently long-lived civilization might treat present astronomy as an archive of a younger cosmos. It might store maps for trillions of years, not because the universe stops being real, because some of its light stops being accessible. Knowledge can outlive the signal that first created it. The traveler may therefore carry history outward. A compact library aboard the spacecraft could contain information from across the observable universe. Images of galaxies that later disappear beyond detection. Measurements of stars that no longer shine. Descriptions of Earth. Languages. music, biology, physics. The spacecraft becomes a vessel not only through space, but through cosmic memory. As billions of years pass, the stars around the traveler evolve. Some expand into red giants. Their outer layers drift into space. White dwarfs remain. Massive stars explode and leave neutron stars or black holes. New generations form from enriched gas. Elements produced inside stars become part of later planets, but the supply of cold gas gradually decreases. Galaxies use it, heat it, expel it, lock it inside long-lived stars and remnants. Star formation declines. The universe enters a slower era. The most enduring ordinary stars will be red dwarfs. They are small, cool, and extremely efficient. Unlike larger stars, many red dwarfs can mix much of their internal hydrogen. They do not leave large unused reserves in their outer layers. They may shine for trillions of years. A planet orbiting such a star could experience an era far longer than the current age of the universe. The future cosmos may belong mainly to these faint stars. A traveler arriving after the sun has disappeared might still find countless red dwarfs glowing quietly. Their light would be dimmer and redder. Their planetary systems may have endured enormous spans of time. Some may have changed through tidal forces, stellar activity, orbital interactions. Others may remain stable. The universe would not become dark all at once. Its brightness would fade gradually. There may be long ages when isolated red stars shine inside increasingly separated galaxies. A spacecraft could travel among them, use their energy, build habitats, move between gravitational systems. The edge of the observable universe would remain unreachable, but the local future could still contain extraordinary complexity. Eventually, even the longest-lived stars exhaust their fuel. The era of active starlight comes to an end. What remains are stellar remnants, white dwarfs, neutron stars, black holes, cooling planets, brown dwarfs, and objects too small ever to ignite sustained fusion. The universe enters a period sometimes described as the degenerate era. The word does not imply disorder in an ordinary sense. It refers to matter supported by quantum effects rather than by active fusion. White dwarfs cool gradually. Neutron stars fade. Planets drift through darkness. Occasional interactions may still produce light. Two stellar remnants may collide. A planet may fall into a compact object. Brown dwarfs may merge and create a new low-mass star. Rare events continue, but the steady background of ordinary stars becomes absent. A traveler surviving into this era would need artificial energy sources. It could collect material around compact objects, use gravitational motion, extract energy from rotating black holes, preserve fuel accumulated earlier, or slow its own internal processes. A machine civilization could reduce activity, wait between events, use energy only when needed. Its experience of time might become very different from biological life. Long intervals could pass in silence. Systems awaken occasionally to repair, observe, communicate, then return to dormancy. The journey across the universe might become a sequence of brief conscious moments, separated by immense cosmic intervals. A traveler attempting to reach a receding destination could remain active for only a tiny fraction of the total voyage. The ship measures position, adjusts course, stores data, then sleeps for millions of years. When it awakens, the sky has changed. Some stars are gone, others have shifted. The target has moved. Expansion has increased the distance. The ship updates its map, then continues. Eventually, the traveler may discover that the destination can no longer be reached. The calculations show that the remaining distance increases faster than the craft can close it. No engine failure occurs. No physical barrier appears. The route simply disappears from the future. The ship continues moving forward, but the target recedes more rapidly through expanding space. A message sent ahead never arrives. A return signal never comes. The traveler has reached the practical meaning of a cosmic horizon. Nothing visible marks the moment. The stars nearby remain ordinary. The instruments continue functioning, but one region of possibility has closed. This may be how the unreachable edge is experienced, not as an arrival, as the gradual recognition that arrival is no longer part of any available future. The spacecraft can choose another destination, a closer remnant, a bound galaxy, a local black hole. The universe still contains paths. Only the original route has ended. As even longer times pass, black holes become increasingly important. They can contain enormous amounts of mass and rotational energy. Matter falling toward them heats and radiates. A civilization may use this energy. It may orbit near a black hole, feed material into an accretion system, or extract energy from rotation through carefully controlled processes. Black holes could become some of the last great power sources. Yet they too are not eternal according to current theory. Quantum effects allow black holes to emit an extremely faint form of radiation. This process is known as Hawking radiation. For a black hole with stellar mass, the temperature is extraordinarily low. The evaporation time is unimaginably long. Larger black holes survive even longer. The supermassive black holes found in galactic centers may persist for times vastly exceeding the current age of the universe. For most of cosmic history, they behave as nearly permanent objects, but given enough time, they gradually lose mass. The smaller they become, the more rapidly the process continues. Eventually, the black hole disappears in a final release of energy. The exact final stage may depend upon a complete theory of quantum gravity. Still, the broad prediction is that black holes do not remain forever. A future traveler could watch the last black hole in its accessible region fade. By then, the universe would have reached an age almost impossible to express meaningfully in everyday numbers. The stars would be long gone. Galaxies would no longer shine. Matter would be thinly distributed. The cosmic background would be colder. Only rare events would interrupt the darkness. This future is sometimes called the Dark Era. It is not an immediate destination. It lies so far ahead that the current age of the universe becomes almost negligible by comparison. The word dark may sound severe, but the physical picture is quiet. An enormous expanding space, faint particles, low energy radiation, occasional remnants, very little free energy available to create change. The universe approaches equilibrium. Differences in temperature become smaller. Useful energy becomes harder to obtain. Complex processes slow. This possible future is associated with heat death. The phrase does not describe the universe becoming infinitely hot. It describes the loss of available energy differences. A machine performs work because energy can move from one condition to another, from hot to cold, from high pressure to low pressure, from concentrated fuel to dispersed products. When energy becomes distributed almost uniformly, fewer processes can use it. The total energy may still exist, but it cannot easily produce organized change. A traveler cannot keep an engine running from energy that is perfectly balanced everywhere. The ship requires a gradient, a source, a sink. As the universe approaches equilibrium, those gradients fade. The journey may end, not because space runs out, because usable change runs out. This is another form of edge, not a boundary in location, a boundary in thermodynamic possibility. The traveler may continue drifting, but cannot accelerate, repair, compute, or maintain awareness indefinitely without available energy. The physical universe persists. The capacity for complex activity diminishes. This distant possibility depends upon the long-term behavior of dark energy, particle stability, and physics not yet fully known. Protons may be stable forever, or they may decay over immense timescales. Dark energy may remain constant, or change. Vacuum states may be permanent, or undergo transitions. The future is calculated from current models. It is not directly observed. Still, these models reveal an important lesson. The journey toward the cosmic edge is also a race against the changing universe. The traveler does not move through an eternal background. The background has a history, a beginning that can be traced, an active era of stars and galaxies, a long fading future. Even an immortal spacecraft cannot assume that useful destinations remain forever. A galaxy visible now may leave the horizon. A star may die. A black hole may evaporate. A source of fuel may disperse. Time changes the map more deeply than motion alone. Could the traveler outrun cosmic history through time dilation? Near light speed, the crew may experience less time. A journey lasting billions of years externally may feel like decades aboard. This allows biological travelers to cross greater distances without aging equally. But it does not preserve the destination. The outside universe still evolves. The travelers arrive in the future. Time dilation does not place them outside cosmic change. It simply changes how much of that change they personally experience. They may close their eyes beneath a young star field, then arrive beneath an ancient one. Their bodies have aged only slightly. The universe has not. A traveler could therefore witness the future in compressed personal time, accelerate close to light speed, travel outward, turn, return. The clock aboard advances modestly. The home galaxy advances enormously. The traveler sees stellar evolution that ordinary observers would need billions of years to experience. In principle, relativistic motion becomes a one-way telescope into the future. But the traveler pays with separation. The people who remained behind are gone. Their descendants may be gone. The civilization may have transformed beyond recognition. The planet may no longer be habitable. The traveler returns not home, but to the location where home once existed. Perhaps an advanced civilization would use this deliberately. Researchers could travel at high speed and return to study the distant future. They would become messengers between eras. Each voyage skips enormous external time. The travelers preserve knowledge from the past. They awaken in a later cosmos, then perhaps depart again. Over repeated journeys, they could cross cosmic history while personally aging very little. But energy and shielding remain. The route cannot be reversed into the past. And eventually, the accessible universe becomes smaller. The travelers cannot leap beyond the event horizon by allowing time to pass. Waiting makes the horizon more restrictive. Destinations continue receding. The time traveler into the future discovers fewer galaxies available. This creates a quiet contrast. Relativity makes distant future eras personally reachable. Cosmic expansion makes distant spatial regions less reachable. Time opens, space closes. The traveler can move far ahead in history, but loses access to much of the map. A civilization may choose between staying connected to a local region and moving into a future where that connection no longer exists. Perhaps the most practical strategy would be to remain inside a gravitationally bound system. The local group will not be pulled apart by dark energy under the standard model. Its merged galaxy and surrounding objects remain available. A civilization could move among them for vast periods. It could gather stars, adjust orbits, store matter, build habitats around long-lived red dwarfs, use compact remnants later. Such engineering is far beyond current humanity, but it does not require crossing the cosmic event horizon. The local universe contains enough material for unimaginable futures. The unreachable edge remains intellectually important. It defines the limit of expansion, but survival and exploration may focus inward, toward the resources that remain bound. A civilization does not need the entire observable universe to create a long history. One galaxy contains billions of suns. One planetary system contains enormous energy and matter. One carefully maintained habitat may continue for longer than human history can easily express. The impossibility of reaching everything does not imply the impossibility of reaching anything meaningful. As the spacecraft continues its imagined journey, the stars behind it grow older. The target ahead becomes redder. The signal from Earth weakens. Messages arrive with greater delay. Eventually, the final communication reaches the craft. It may contain a farewell, or a simple scientific update, or the recorded sound of rain on a world that no longer exists. The travelers preserve it. They continue forward. Their ship carries a small memory of a bright cosmic era. Around them, the universe expands quietly. The edge remains absent. No wall appears. No final boundary approaches. Only new horizons, changing stars, and the steady movement of time. The next part of this journey will explore whether any civilization, natural phenomenon, or form of information could leave the observable universe, what it means for something to cross a horizon, and whether the universe itself can contain events that forever disappear from every possible observer. A horizon does not destroy what crosses it. It changes who can receive information from it. This distinction is essential. When a distant galaxy moves beyond Earth's cosmic event horizon, the galaxy does not encounter a wall. Its stars continue shining. Its planets continue orbiting. Any observers living there continue measuring their local universe normally. Nothing dramatic needs to happen at the moment causal contact is lost. The separation is defined by the future paths available to light. A signal emitted there at a sufficiently late time can no longer reach Earth. A signal emitted from Earth can no longer reach the galaxy. The two regions continue existing. They simply no longer share a communicative future. From Earth's perspective, the last arriving information becomes increasingly stretched. Each later signal takes longer to arrive. Its wavelength grows, its energy decreases. Events appear slowed, The distant region fades towards silence, but from the distant galaxy's perspective, its clocks remain ordinary. Its light still moves locally, at the speed of light. Nearby stars look normal. The fading occurs in our relationship with it, not within the galaxy itself. This makes a cosmic horizon deeply observer-dependent. Earth has one horizon. A civilization in another galaxy has another. A spacecraft traveling between them develops its own changing region of possible communication. There is no single universal shell that every object crosses at the same moment. A galaxy may lie beyond Earth's future reach, while remaining fully connected to nearby systems. Its inhabitants may communicate across their own local region for billions of years. They may observe galaxies hidden from Earth. They may possess a cosmic map partly different from ours. Every observer receives one portion of the universe. No one receives all of it. Could a spacecraft leave the observable universe? The question depends upon what the phrase means. The observable universe is centered on the observer. A spacecraft cannot simply fly beyond its own observable universe, because its observable region moves with it. Wherever it travels, light continues arriving from a surrounding portion of space-time. The craft always remains at the center of its own past light cone. New regions may become visible ahead. Old regions behind may become unreachable. But the spacecraft does not step outside observation itself. It carries a new observational horizon. From Earth's viewpoint, however, a spacecraft can eventually move beyond the region from which its later signals can return. Earth may continue receiving older transmissions for a long time. Those signals become weaker and more delayed. Eventually, no new information arrives. The spacecraft has not left all reality. It has left Earth's causal future. Its mission may continue, its instruments may operate, its travelers may live, but Earth can no longer know what happens next. The craft becomes part of a history that continues beyond our access. This is one of the quietest meanings of departure. A ship may not be destroyed. It may simply become unknowable from home. Imagine that the spacecraft carries an archive of Earth, languages, maps, scientific knowledge, images of oceans, the sounds of forests, the names of people who lived long ago. As the craft travels outward, it transmits copies home. At first, the messages arrive regularly. Then the interval between them grows. A daily report may arrive weeks apart. Later, years apart. The signal shifts toward lower frequencies. Its energy thins across expanding space. The receivers on Earth grow larger and more sensitive. They collect the final fragments. Then the transmission fades below detection. The archive aboard the ship still exists, but Earth has no later evidence of its condition. Perhaps the spacecraft reaches another star. Perhaps it repairs itself. Perhaps its descendants build a settlement. Perhaps it fails quietly in intergalactic space. All possibilities remain outside our knowledge. Once communication ends permanently, no observation from Earth can distinguish them. This is not ordinary uncertainty. Ordinary uncertainty may be solved by waiting. A delayed message eventually arrives. A hidden object can be approached. A better instrument may detect a faint source. Beyond a true event horizon, waiting does not help. The information is not merely late. It is absent from every future event accessible to the observer. No telescope becomes powerful enough. No antenna becomes sensitive enough. The path itself does not connect. This gives horizons a special place in physics. They define not just what is difficult to know, they define what can never be known from a particular region. Black holes provide another example. Matter falling toward a black hole crosses an event horizon. From far away, its light becomes increasingly redshifted and delayed. The object appears to fade. Locally, however, the falling object may cross the horizon without encountering a physical surface, especially around a very large black hole, where tidal forces at the horizon can be modest. The decisive change is causal. After crossing, no light signal sent by the object can escape to distant space. Its future remains inside the black hole. The cosmological horizon works in the opposite directional sense. A black hole horizon prevents signals inside from reaching the exterior. A cosmic event horizon prevents sufficiently distant future signals from ever reaching the observer. Both divide space-time according to communication. Neither must look like a wall to someone crossing locally. Yet the two horizons arise from different geometries. A black hole is associated with concentrated gravity. A cosmological horizon is associated with the large-scale expansion of the universe. One surrounds a collapsed region. The other surrounds an observer's accessible future within expanding space. Their similarity lies in causality. Information can travel only along allowed paths. Once every path leads away from an observer, communication ends. Does the information itself disappear? This question reaches into one of the deepest areas of modern physics. In everyday physical processes, information is not usually imagined as being destroyed. A glass may shatter. The original arrangement becomes difficult to reconstruct, but in principle, the motions and interactions of the fragments contain traces of what happened. A drop of ink spreads through water. The pattern seems lost, yet the microscopic state still evolves according to physical laws. Information becomes dispersed, not necessarily erased. Black holes made this question more difficult. If matter falls into a black hole, and the black hole later evaporates through Hawking radiation, what happens to the detailed information describing the matter? Early descriptions suggested that the outgoing radiation might be purely thermal. If so, the original information could be lost. That possibility conflicts with important principles of quantum mechanics. The resulting debate became known as the black hole information problem. Many physicists now expect that information is preserved in some subtle form, perhaps encoded within correlations in the Hawking radiation, perhaps described through deeper relationships between gravity, quantum theory, and space-time. But a complete, experimentally verified account remains unfinished. Cosmological horizons raise related questions. Information may cross beyond an observer's horizon and become permanently inaccessible to that observer. Whether it is lost globally is a different matter. Other observers may still receive it. The information may continue existing within another region. The horizon removes access. It does not automatically prove destruction. Suppose a star beyond Earth's horizon emits a photon. That photon travels locally through its own surrounding space. It may be detected by a nearby civilization. It may interact with dust. It may enter a telescope elsewhere. Earth never receives it. From our viewpoint, that photon contributes nothing to future observation. From another viewpoint, it may carry valuable information. The universe can preserve information while distributing it into regions that can no longer compare records. Knowledge becomes separated. One observer has one fragment. Another observer has another. No signal joins the fragments again. Could an event become hidden from every possible observer? An event normally occurs within some local region. Nearby matter can interact with it. Light can leave it in at least some directions, unless a horizon or extreme geometry prevents this. Observers inside its future light cone may receive evidence, but cosmic expansion can carry different regions apart so that no single observer collects all events. There may be no universal archive, no location from which the complete history of the universe becomes visible. Some events influence only a limited domain. Outside that domain, they leave no trace. Inside it, they may be recorded. If the local records are later destroyed or carried across horizons, the event may become practically unrecoverable. Yet saying it vanished from all reality would go beyond what observation can establish. The safer conclusion is that information can become permanently inaccessible to every observer within a particular causal region. Another region may retain it, or perhaps no surviving record remains. The distinction cannot always be tested from here. This means the universe may contain countless histories that never enter Earth's story. A star may form beyond our horizon. Planets may develop around it. A civilization may discover mathematics, build cities, observe its own sky, and disappear. No photon from those events ever reaches us. No gravitational wave, no particle, no consequence. For Earth, that entire history is absent, not hidden behind noise, not waiting to be discovered, causally disconnected. The civilization's existence may still be real. Reality does not require our observation, but science on Earth cannot confirm its individual story. The most we can do is infer that similar regions may exist if the universe continues beyond our horizon. This is a humbling feature of cosmology. The observable universe is not selected because it contains everything important. It is selected because its information reached us. Another observer's universe may include wonders forever absent from ours. Their greatest discoveries may concern galaxies Earth can never see. Their unanswered questions may involve regions visible only to them. Every civilization studies one cosmic window. No window is the entire building. Could information be sent beyond the universe itself? There is no known physical meaning to that operation. A message travels through space-time. If the universe means all space-time and physical reality, there is no ordinary external location toward which the signal can be aimed. A radio wave needs a path. A laser needs a direction. A spacecraft needs a future trajectory. Without a defined external space-time, the phrase outside the universe does not describe a destination in known physics. A signal can leave Earth, leave the solar system, leave the Milky Way, leave the local group. It may cross Earth's cosmic horizon, but at every stage, it remains within the universe. It continues through whatever space-time exists along its path. Leaving our observable region is not leaving reality. It is leaving one observer's access. This is similar to a ship passing beyond the ocean horizon. The ship leaves sight, not the ocean. The cosmic version is more permanent because expansion may prevent any return. But the basic distinction remains. A limit of visibility is not necessarily a limit of existence. The universe may also contain regions created through processes, such as inflation, that never communicate with ours. If such regions exist, they may possess their own observable histories. Calling them separate universes can be useful in some theoretical discussions, but the language may suggest a clear boundary or external space that the theory does not provide. They may instead be causally disconnected domains within a larger structure. No verified method allows a traveler to leave one and enter another. The separation may be built into the expansion of space-time itself. Even a light beam cannot cross it. Such ideas remain theoretical. They illustrate how causality can divide reality without requiring solid walls. Two regions may belong to one broader mathematical structure while sharing no signals. For every practical purpose, each becomes a universe to its own observers. A civilization might attempt to preserve information against this separation. It could send many copies in many directions. Some remain local, others travel outward. Every colony receives an archive. Each creates additional copies. The information spreads like seeds. Cosmic expansion eventually isolates the branches. But the archive survives in several causal regions. No single branch knows the full future of the others. They share an origin, then diverge permanently. Over immense time, the copies change, languages evolve, records are interpreted differently. Some archives are preserved carefully, others are lost. A single human history becomes many distant traditions. The universe prevents reunion, yet it allows inheritance. Information can cross space before horizons close. Once established in another region, it becomes part of that region's future. This may be the closest a civilization comes to leaving its observable universe. It does not send one traveler beyond reality. It sends descendants beyond future contact. The parent civilization watches the signals fade. The distant branch watches the parent fade as well. Each continues beneath a different sky. Neither can return. The shared past remains their final connection. Natural processes already perform something similar. Photons leave stars. Neutrinos escape exploding stellar cores. Gravitational waves spread from merging black holes. Each messenger carries information outward. Some enters regions that later become causally separated. The universe continuously distributes traces of events. Most are never collected. A photon may travel for billions of years without encountering a detector. It may be stretched until its energy becomes almost negligible. It may eventually cross a horizon relative to one observer, while remaining available to another. Information flows through a web of possible futures. Only a tiny portion ends inside scientific instruments. Observation is therefore an act of interception. A telescope does not summon distant light. It waits where the light happens to arrive. The photon completes an ancient route. The detector records it. A connection that might never occur again becomes data. The farther the source, the more remarkable the intersection. A particle leaves a galaxy before Earth forms, crosses expanding space, passes countless regions, then enters a mirror or sensor built by a temporary civilization on one small planet. For that brief moment, two distant histories meet. Once recorded, the information can be stored, copied, studied, shared. The galaxy may later disappear beyond reach, but part of its past remains here. Astronomy creates local memories of places the universe is slowly removing from contact. Perhaps this is why the present sky feels so rich. Humanity lives while vast numbers of galaxies remain observable. Their light fills our instruments. The universe has not yet hidden them. The information can be collected before it fades. Future civilizations may inherit images of regions they can no longer detect directly. Our telescopes become bridges across time, not permanent bridges. Records of bridges that once existed. A civilization traveling far from Earth would carry such records. Its new sky might contain different galaxies, different horizons, different ancient light. The travelers could compare what they see with what Earth once saw. The combined archive would reveal a larger portion of the cosmos than either location alone. But transmitting the new observations home may eventually become impossible. Knowledge expands locally, while the shared network breaks apart. There is a limit to collective cosmic science. Observers can cooperate only while signals connect them. Beyond that, discovery continues separately. No final library gathers everything. The universe may be knowable only in fragments. This fragmentation does not mean the laws of physics change randomly from place to place. The same broad principles may operate throughout. Light follows local geometry. Matter responds to forces. Stars form from gas. Entropy increases. But the events shaped by those laws remain distributed. One region knows one history. Another region knows another. The total reality may exceed every possible account of it. Could a perfectly advanced observer reconstruct the whole universe from local information? Probably not, if permanently disconnected regions leave no measurable influence. No amount of intelligence extracts data that never entered the observer's causal past. A calculation can extend a theory beyond observation. It can estimate likely conditions. It cannot recover the exact arrangement of every unseen galaxy without evidence. The laws may predict possibilities. They do not identify which possibility occurred in a region that never communicated with us. Perfect reasoning does not replace missing information. A horizon is therefore also a limit on prediction. The future of a disconnected civilization cannot be known from Earth. Its local decisions, accidents, discoveries, and biological changes depend upon details unavailable here. Even if the broad cosmology is understood, the individual story remains open. The universe preserves freedom for distant history through separation. As the imagined spacecraft continues outward, its crew watches Earth's signals fade. The sun becomes one star among many. Then the Milky Way becomes a small luminous structure behind them. Messages from home arrive from earlier and earlier chapters relative to the travelers present. Eventually, the final signal enters the receiver. It may be a simple pulse, a timestamp, a confirmation that Earth still existed when the message began. After that, silence. The travelers know that home may continue. They also know that no later news can reach them. Their own transmissions may never return. The separation is complete. Around the spacecraft, local physics remains unchanged. The instruments measure stars. The engines adjust course. The travelers speak, sleep. Remember, nothing announces that one cosmic relationship has ended. The horizon is crossed quietly. The ship does not leave the universe. It enters a future no longer shared with Earth. This may be the most accurate way to imagine departure beyond the observable world, not falling through an outer boundary, not entering absolute nothingness, simply continuing until communication becomes impossible. The travelers remain somewhere. Earth remains somewhere. But somewhere is no longer enough to connect them. Space and time have placed their histories apart. The next and final part of this journey will return to the original question, gathering together the speed of light, cosmic expansion, relativity, horizons, and the unknown shape of space to understand why the edge of the observable universe is not a destination and why the unreachable cosmos still matters deeply to those who remain beneath the stars. The observable universe has an edge only in the sense that human vision, instruments, and information have limits. It is not known to possess a final wall. No distant surface marks the end of space. No last galaxy waits beside an exterior darkness. Instead, the boundary is created by the history of light. There has been only a finite amount of cosmic time for signals to travel. Everything visible lies within the region whose information has been able to reach us. Everything beyond remains outside our present observation. Some of it may become visible later, some of it never will. This is the first reason the edge cannot be reached. It is not a fixed location, it is an observer's horizon. A civilization in another galaxy sees a different observable universe. Its horizon surrounds its own position, It receives ancient light from regions arranged around it. Some of those regions are invisible from Earth. At the same time, Earth may see places hidden from that distant civilization. Neither observer occupies the center of all reality. Each occupies the center of one sphere of received information. A spacecraft moving away from Earth does not approach one universal boundary. Its horizon changes with its position. New regions may enter view. Others become more difficult to communicate with. The traveler carries a moving window through space-time. The window never becomes the whole universe. Imagine once more the horizon across a calm ocean. From the shore, a line appears where sea and sky meet. A ship travels toward it. The line does not grow closer in the expected way. The ship reaches water that once appeared near the horizon. Then another horizon forms farther ahead. The visual limit moves with the observer. The cosmic version is not caused by Earth's curvature. It comes from time, light, and expansion. But the lesson is similar. A boundary of sight is not always a destination. The second reason the edge cannot be reached is the speed of light. Matter can approach this speed. It cannot reach or exceed it through ordinary motion. The closer a spacecraft comes, the more energy additional acceleration requires. At the limit, the required energy becomes infinite. No engine can provide it. No fuel supply can contain it. Relativity allows travelers to experience time differently. A journey lasting millions of years outside the craft may feel much shorter aboard it. Distances in the direction of travel appear contracted. The travelers may cross remarkable regions without personally aging by the full external duration. But relativity does not remove the speed limit. It does not place the spacecraft beyond causality. The ship still follows a path through space-time. Only destinations connected to that path can be reached. Time dilation changes the traveler's experience. It does not create a route where no route exists. A crew might leave Earth and experience a few decades while the wider universe ages by billions of years. They would arrive not at the young galaxy seen through a telescope, but at its distant future. The original stars may be gone. The galaxy may have merged. Its planets may have changed. The photograph that inspired the journey belonged to the past. The spacecraft can never arrive inside that photograph. It reaches only what the source has become. Every long-distance journey is therefore also a journey into time. The farther the destination, the more ancient its observed image. The longer the trip, the more distant its condition at arrival. Near the observable horizon, these two versions may be separated by most of cosmic history. The edge visible from Earth is an ancient edge. Any arrival would belong to an unimaginably later universe. The two cannot coincide. The third reason the edge cannot be reached is cosmic expansion. Space between unbound galaxy groups grows. The greater their separation, the more rapidly the distance tends to increase. Across sufficiently large scales, the total recession can exceed the speed of light. This does not mean galaxies locally break relativity. Nearby observers still measure light moving normally. The faster-than-light value describes the change in a vast distance across expanding space-time. Old photons may still reach Earth from such regions. They began their journeys when the universe was smaller. Their paths crossed a changing geometry successfully. But a new signal sent today may never complete the same route. The destination has moved farther away. Expansion has altered the future. This is why the observable universe is much larger than the region humanity can ever influence. Ancient light reaches us from galaxies whose present condition is already beyond communication. We see their past. We cannot send a message into their future. A civilization there may look toward the ancient Milky Way while being equally unable to contact modern Earth. Two worlds can remain visible to one another through old light while having no shared future conversation. The universe allows observation to continue after accessibility has ended. This creates the cosmic event horizon. It does not glow. It does not block the spacecraft with a material barrier. It marks a limit in cause and effect. Beyond it, no signal sent now can ever arrive. A destination outside that horizon is not merely difficult to reach. It is absent from every future path available to Earth. A faster engine below light speed cannot help. A longer waiting period makes the separation greater. The limitation belongs to space-time itself. This is a deeper obstacle than distance. A mountain can be crossed, an ocean can be sailed, a distant planet can, in principle, be approached. A causal horizon is not an object placed in the path. It is the absence of a connecting path. The traveler cannot break through because there is no surface to break. The destination and the traveler simply do not meet anywhere in the future geometry. The fourth reason the edge cannot be reached is that the entire universe may have no edge. Space may be infinite. In that case, every distance crossed leaves more distance ahead. There is no last cluster, no final star, no complete crossing. A spacecraft could travel forever without approaching an outer boundary. Or the universe may be finite but unbounded. Space may close upon itself through global geometry. A traveler moving in one direction might eventually return to the starting region. No wall would appear, no exterior would be entered. The route would continue within the same space. Even then, cosmic expansion might prevent the journey from being completed. The path may lengthen faster than the traveler advances. A finite universe does not guarantee that it can be circled, and a nearly flat observable region does not reveal the full global shape. The total cosmos may be vastly larger than the part available to measurement. Its geometry may be so gentle that no curvature can be detected within our horizon. Its topology may connect distant regions in ways whose repeating patterns have not yet reached us. Or space may simply continue without end. Current observations do not reveal a nearby boundary. Every reliable map shows more universe rather than the beginning of an exterior. The fifth reason is that looking farther does not reveal farther space alone. It reveals earlier time. The oldest electromagnetic light is the cosmic microwave background. Beyond it lies not a wall, but an era when the universe was opaque. Photons scattered through hot plasma. Clear images could not travel freely. The microwave background marks the time when matter cooled enough for light to move across the cosmos. It is a surface of ancient visibility, not a surface a spacecraft can visit. The young universe is no longer waiting far away. It happened everywhere. The matter around Earth was also part of that hot early state. Traveling outward cannot return a spacecraft to it. A telescope looks into the past because light required time to arrive. A spacecraft moves into the future because its journey also requires time. Observation and travel point in opposite temporal directions. The deeper the telescope sees, the younger the image becomes. The farther the spacecraft travels, the older the universe becomes at arrival. No motion through space allows a traveler to catch the early universe. Other messengers may reveal earlier stages. Neutrinos, gravitational waves, subtle relics preserved in later structures. Scientific instruments may move the horizon of knowledge backward, but this remains observation, not physical arrival. The universe reveals its early history through evidence carried forward. Humanity approaches the beginning by reading traces, not by traveling to a distant location. The sixth reason concerns the future. The universe continues changing during every imagined voyage. Stars exhaust their fuel. Galaxies merge. The supply of gas for new stars declines. Distant galaxies fade beyond observation. The cosmic microwave background stretches toward longer wavelengths. A traveler moving for billions of years enters a cosmos increasingly unlike the one left behind. Far in the future, the local group remains as one gravitationally bound island. Most external galaxies disappear from view. The sky becomes emptier. Later, the longest-lived stars fade. Stellar remnants dominate. Black holes persist for extraordinary periods. Then they too may slowly evaporate. The journey toward the cosmic edge becomes a journey through the life of the universe itself. Even an extremely durable spacecraft cannot assume that stars, destinations, or usable energy remain unchanged. A target may cease shining. Its galaxy may merge. Its region may move beyond reach. The available map narrows while the traveler continues. Eventually, thermodynamics becomes a greater obstacle than distance. Engines require energy differences. Life requires organized flows of energy. Computation requires physical change. As the universe approaches a more uniform state, usable energy becomes harder to find. Space may continue. The ability to travel meaningfully may not. The final boundary may therefore be neither a wall nor a horizon. It may be the fading of every practical means of motion, repair, observation, and memory. Yet these distant limits do not make exploration insignificant. The accessible universe remains almost beyond comprehension. The Milky Way alone contains hundreds of billions of stars. The local group contains many galaxies and an enormous range of environments. Even at a small fraction of light speed, A patient civilization could visit countless systems. It could send probes, build observatories, create habitats, study planets, map black holes, preserve knowledge. No journey to the observable edge is required for the cosmos to remain inexhaustibly rich. A single planetary system can contain worlds, moons, asteroids, magnetic fields, atmospheres, and histories that require generations to understand. One galaxy may contain more destinations than any civilization can visit individually. The unreachable universe does not reduce the value of the reachable one. It gives that local region a clearer meaning. Humanity does not possess the whole cosmos. It possesses one temporary window. Through that window, ancient photons arrive. They cross billions of years. They enter mirrors, antennas, and detectors. They become images and measurements. Each observation connects Earth with a place no spacecraft may ever approach. A distant galaxy may already be beyond every future message we can send. Still, its light reaches us tonight. That light carries information about stars, gas, gravity, chemistry, and the development of cosmic structure. The connection is one way, but it is real. Perhaps this is how the edge is truly explored. Not by standing upon it, by receiving what crossed it. Telescopes become vessels that travel without moving. They collect photons whose journeys are far longer than any human mission. A detector on Earth can receive information from a region separated by tens of billions of light years. The instrument does not cross that distance. The light completes the voyage. Humanity waits at the destination. A radio telescope listens to faint wavelengths stretched by cosmic expansion. An optical telescope gathers individual photons from early galaxies. A gravitational wave observatory measures distortions created by distant collisions. Each instrument allows the universe to come toward us. This form of exploration is quieter than travel. It does not require engines. It requires patience, sensitivity, careful interpretation, and the understanding that every signal belongs to another time. Future telescopes may reveal the atmospheres of distant Earth-like planets. They may identify chemical combinations associated with life. They may map the earliest galaxies. They may detect gravitational waves from the first moments of cosmic history. They may discover phenomena for which no current category exists. The observable horizon will remain, but the amount of knowledge gathered inside it can continue growing. A physical limit does not imply an intellectual end. The edge may remain unreachable. Its light may still teach us. This distinction gives cosmology its unusual character. It studies places that cannot be visited, times that cannot be entered, objects that no longer exist in the form observed, and regions that may already be beyond all future influence. Yet the science remains precise. Distances can be estimated, expansion can be measured, the early universe can be reconstructed, possible futures can be calculated. Knowledge reaches where bodies cannot. The traveler imagined throughout this journey may continue moving. Perhaps the craft remains within the local group. Perhaps it visits another star. Perhaps it becomes one link in a chain of settlements extending through the galaxy. No crew reaches the final edge, but each destination changes the view. From another star, Earth becomes a faint point. From another galaxy, the Milky Way becomes an external spiral. From every location, a new horizon surrounds the observer. New ancient light arrives. The universe reveals another fragment of itself. There is no privileged final viewpoint, only many local perspectives. A civilization spread across stars could combine these perspectives while communication remains possible. Its map would become richer than Earth's alone, but still incomplete. Eventually, expansion may separate the distant branches. Their observations continue independently. No central archive receives everything. The full universe remains larger than any one history. Perhaps no observer is meant to see all of reality. Not because the universe has intentions, because causality gives every observer a limited past. A mind exists at one location. Signals arrive along finite paths. Knowledge forms from those arrivals. The limitation is shared by every possible civilization. Even one with technology far beyond ours remains inside space-time. It may see farther, travel faster, live longer, and manipulate matter with extraordinary precision. But it cannot receive information from a region that never enters its causal past. Intelligence expands what can be understood. It does not abolish every horizon. There is a gentle honesty in this. The universe does not promise complete access. It offers evidence, patterns, partial views, and enough consistency for minds within it to reconstruct a remarkable story. From one small planet, humans have learned that galaxies recede, that space expands, that the observable universe is roughly 93 billion light-years across in present distance terms, that the oldest visible light comes from a time before stars, that distant regions can be visible while remaining forever unreachable, and that the entire universe may extend far beyond everything we can observe. These discoveries required no journey to the edge. They came from light arriving here, from equations tested carefully, from instruments refined across generations, from human beings looking upward and asking what the darkness contains. The answer is not a final boundary. It is a layered cosmos of horizons. The particle horizon marks the reach of past information. The cosmic event horizon limits future contact. The microwave background marks the oldest freely traveling light. Relativity limits material motion. Expansion changes every distant route. Geometry determines whether space is finite, infinite, flat, or globally connected. Thermodynamics shapes the ultimate future. Each horizon answers a different question. Together they explain why the simple idea of reaching the edge dissolves. There is no single edge to reach. There is only a changing relationship between observer, information, and space-time. The farther science follows that relationship, the more subtle the universe becomes. A wall would be easier. A wall has a position. It can be approached, measured, perhaps crossed. A horizon is more mysterious. It depends upon where the observer stands, when the journey begins, how the universe expands, and whether light can connect two events. It is invisible, yet it decides the possible future. A wall separates two nearby places. A horizon separates two histories. As this journey comes to an end, allow the enormous scale of the cosmos to soften once more. There is no need to imagine every distance at once. No mind can hold 93 billion light-years as an ordinary picture. The numbers describe relationships. The time light has traveled, the expansion it crossed, the ancient regions whose messages are only now arriving. Outside, the night remains quiet. Stars appear fixed. Galaxies are hidden from unaided sight. The cosmic expansion produces no sound. Horizons pass no visible line across the sky. Yet the universe continues unfolding. Photons complete journeys that began before Earth existed. Distant galaxies move beyond future contact. Nearby stars continue their slow lives. And this small planet travels gently through one gravitationally bound galaxy. The unreachable edge does not need to feel like a loss. There was never a promise that all of reality could become one destination. The universe can be meaningful without being fully crossable. Its limits give shape to every possible journey. They tell us where communication can travel, which histories can meet, and which ancient light has arrived against extraordinary distance. Humanity may never stand at the edge of the observable universe, but every clear night places us at the center of one observable universe. Not the center of all existence, the center of the information reaching this moment. Light arrives from every direction, from the moon after a little more than a second, from the sun after several minutes, from nearby stars after years, from galaxies after millions or billions of years, and from the early cosmic glow after almost the entire age of the universe. All of those journeys end here. For a brief time, their information becomes part of one human view. The edge remains far away. Perhaps it is not a place at all. Perhaps it is simply the final limit of what can reach us. Beyond it, space may continue, galaxies may shine, worlds may turn, and histories may unfold without ever touching ours. Within it, there is already more wonder than any civilization could finish exploring. Let the distant galaxies fade gently into the background now. Let the imagined spacecraft become a small point among the stars, its engines quiet, its windows filled with ancient light. There is no need to follow it farther tonight. The universe continues without requiring an ending. The horizon remains around every observer, and here, beneath the familiar sky, there is time to rest. Sleep well, and good night.